Hey everyone! Welcome to Algebra 1. Today, we are kicking off Chapter 1, Working with Real Numbers. Here is our roadmap. We have sections 1.1, 1.2, 1.3, and 1.4. But for today, we are going to dive straight into section 1.1, Sets and Expressions. Let's get started. A set is a collection of objects. Each object in the set is called an element or a member. You use the symbol epsilon to show that something is a member of a set. The symbol means the opposite, it is not a member of. Sets are usually named by capital letters. The elements of a set are enclosed in braces. For example, A equals the set containing 1, 3, 5, and 7. The universal set, denoted by the symbol U, is the set of all objects under consideration. So in a math course, the universal set often consists of all numbers. To understand sets, let's imagine a pizza. A pizza is a collection of toppings. Each topping is an element of that pizza. Pepperoni is on the pizza, so it is an element of pizza A. But pineapple is not on this pizza, so it is not an element. We name our pizza with a capital letter, like A. And we list all the toppings inside braces. Pizza A equals pepperoni, olive, and mushroom. Finally, the universal set U is like the entire kitchen menu. It contains all possible food items under consideration, including pizzas, pastas, and drinks. Let's work on a practice problem. Given that set B equals 3, y, 7, and alpha, determine whether each statement is true or false. For A, y is an element of B, so the statement is true. For B, 7 is also an element of B, so it is also true. For C, 3 is an element of B, meaning 3 not in B is false. Finally, for D, 5 is not an element of B, so the statement is false. An empty set, or null set, is a set without any elements or members. It is denoted by the slash symbol or empty braces. A subset is a set whose elements are all contained in another set. The horseshoe symbol means is a subset of. Remember two important rules. Any set is a subset of itself, and the empty set is a subset of any set. To understand the empty set, imagine an empty transparent bag. Because there is absolutely nothing inside it, it represents the empty set. Now, imagine a smaller bag placed entirely inside a larger bag. This small bag is a subset of the big bag, meaning everything in it belongs to the larger one. Think about it. Any bag contains its own items, so it is a subset of itself. And an empty space is always inside any bag, so the empty set is a subset of every set. Let's check our understanding with a practice problem. Given that set C equals 2, A, and 5, determine whether each statement is true or false. For A, the set containing 2 is a subset of C, so it is true. For B, 5 is an element, not a set, so using the subset symbol makes it false. For C, any set is a subset of itself, so it is true. Finally, for D, the empty set is always a subset of any set, so it is also true. In Algebra 1, the sets used are usually subsets of the real numbers. The set of real numbers, denoted by R, consists of all numbers on the number line, including integers, decimals like -1.1 and +1.5. The following are standard subsets of R: natural numbers starting from 1, whole numbers including 0, and integers which include all whole numbers and their negatives. Let's test our understanding with a practice problem. Given the subsets of real numbers, determine whether each of the following statements is true or false. For A, all natural numbers are contained in whole numbers, so it is true. For B, whole numbers only include 0 and positive integers, so -3 and W is false. For C, 1.5 is a decimal and all decimals belong to real numbers, so it is true. Finally, for D, natural numbers start from 1, meaning 0 is not an element, so it is false. A rational number is a number that can be expressed as a fraction p over q, where p is an integer and q is a natural number. For example, 0.25 can be written as 1/4. An irrational number is a number that cannot be expressed in that fractional form. For example, the famous mathematical constant pi is approximately 3.1415, which goes on forever without repeating. Both the set of rational numbers q and irrational numbers I are subsets of the real numbers R. Let's test our skills with a practice problem. Identify whether each statement about rational and irrational numbers is true or false. For A, 0.25 can be written as 1/4, which is a fraction, so it is true. For B, pi is an irrational number because it cannot be written as a fraction, so the statement is false. For C, the square root of 2 is a non-repeating infinite decimal, so it belongs to the irrational set, which is true. Finally, for D, a number cannot be both rational and irrational at the same time, so their intersection is the empty set. This is true. The union of sets A and B, denoted by union V, is the set of all elements in either A or B or both sets. Let's look at an example. Suppose set A equals 2, 5, 7, and 12, and set B equals 5, 7, 10, and 18. Find a union V. Elements are not counted twice. They are either in or out. So 5 and 7, which are in both A and B, only appear once in the union. Therefore, a union V is 2, 5, 7, 10, 12, and 18. To understand a union, let's imagine ordering a half and half pizza with a friend. Set A is your favorite toppings and set B is your friend's toppings. The union is the final pizza containing all requested toppings combined. What if both of you choose olives? The pizza place won't dump a double amount of olives to ruin the pizza. Olives are simply placed on it once. In a union, shared elements only appear once. So, if your toppings are pepperoni and olive, and your friends are olive and mushroom, the total union pizza is simply pepperoni, olive, and mushroom. Let's test our skills with a comprehensive practice set. Given 4 distinct sets, A, B, C, and D, find the union for each of the following questions. For number 1, combining sets A and B and listing them in order gives 0, 1, 3, 4, 5, 7, and 8. For number 2, we list the combined elements from smallest to largest, making sure the shared 6 appears once. For number 3, sets A and C share 3 and 5, so we list them once in order. Finally, for number 4, combining B and D and arranging them from smallest to largest gives 0, 1, 4, 6, and 7. The intersection of sets A and B, denoted by A intersection B, is the set of all elements that are in both set A and set B. Let's look at example 2. Let set A equal 3, 8, 11, and 24, and set B equal 1, 8, and 15. Find A intersection B. Only the number 8 is in both A and B. So, A intersection B equals the set containing 8. To understand an intersection, let's imagine finding a time to hang out with a friend. Set A is the hours you are free, and set B is the hours your friend is free. The intersection is the specific time you can actually meet. If you are free at 3, 8, 11, and 24, and your friend is free at 1, 8, and 15, you cannot meet at 3 or 1. You must pick 8 o'clock because it is the only hour you both share. In math terms, your schedule intersected with your friend's schedule leaves only 8. Therefore, A intersection B equals the set containing 8. Let's check our skills with a practice problem. Given two distinct sets, A and B, find the intersection of the two sets. Looking at both sets, only the numbers 4 and 9 appear in both A and B. Listing them from smallest to largest, A intersection B equals the set containing 4 and 9. A numeric expression contains only numbers. Since there are no unknown quantities, you can always work out its exact value. For example, 1.05 times 4 evaluates to exactly 4.2. Numeric expressions with the same value are like different names for the same thing. All these expressions have the exact same value of 4.2. 1.05 times 4, 4 plus 0.2, and 5 minus 0.8. Because they describe the exact same thing, you can always substitute one for another. If you see 1.05 times 4 somewhere, you can write 4 plus 0.2 instead. Let's check our understanding with a practice problem. 3 of the following numeric expressions evaluate to the exact same value. Identify the one that does not belong. Let's calculate each expression. A, B, and C all evaluate to exactly 3.5. They are different names for the same value. However, expression D evaluates to 2.5, which is not equal to 3.5. Therefore, D is the correct answer because it does not have the same value. A lot of the time in math, you can use letters to stand for unknown amounts. For example, if you were not sure how many inches long your desk was, you could just call the length x inches. When you see letters in equations, they are just numbers that you don't know the value of yet. Letters that represent unknown numbers are called variables. To make it easier, think of a variable as a mystery gift box. The letter X is just a label written on the outside of the box. We don't know what number is hidden inside yet. Depending on the situation, the box could hold a 5, a 10, or any other value. Once we solve the math puzzle, the box opens up to reveal its secret number. Let's test our knowledge with a practice problem. Which of the following is an algebraic expression that contains a variable? Let's analyze the options. Expressions A, C, and D contain only numbers and operations, which means they are numeric expressions, not algebraic. However, expression B contains the letter x, which is a variable representing an unknown number. Therefore, B is an algebraic expression and is the correct answer. A coefficient is a number that multiplies a variable. In the algebraic expression 3x, the number 3 is the coefficient of x. Think of the variable x as a single mystery box containing candies. If you have 3x, it simply means you have 3 identical mystery boxes. The coefficient tells you the count of the boxes. If each mystery box holds 5 candies, 3 times 5 gives you 15 candies in total. The coefficient multiplied the value inside. Let's check our understanding with a quick practice problem. In the algebraic expression, negative 5x plus 7, identify the coefficient of x. Remember, a coefficient is the number that multiplies a variable. Here, the number multiplying x is negative 5, not just 5. The negative sign stays with the coefficient. Therefore, the coefficient of x is negative 5. Welcome back, everyone. Today, we are exploring working with real numbers. In this unit, we cover several core areas including sets and expressions, the real number system, exponents, roots, fractions, and mathematical logic. For today's lesson, we are going to focus entirely on our second topic, the real number system. Let's dive in. The real number system is based on simple rules. It relies on the existence of a set of numbers plus 2 binary operations. In Algebra 1, the set of numbers used is the real numbers, denoted by R, and the 2 binary operations are addition and multiplication. Next, let's explore the properties of equality that always hold true for any real numbers A, B, and C. First, we have the reflexive property, which states that A equals A. Second, the symmetric property means if A equals B, then B equals A. Finally, the transitive property states that if A equals B and B equals C, then it equals C. Think of a binary operation like a magic blender. You put 2 separate ingredients inside, and it combines them to create one brand new dish. Now, let's look at equality. The reflexive property is like looking into a mirror. An object always looks exactly like itself, just as A always equals A. The symmetric property is like a perfectly balanced seesaw. If the left side is equal to the right side, we can swap their places, and it still stays perfectly balanced. Finally, the transitive property is like a chain reaction. If block A connects to block B, and block B connects to block C, then block A is automatically connected to block C. Let's try a practice problem together. Look at the statements on the screen. If x equals y and y equals 5, then x equals 5. Can you identify which property of equality is being used here? Take a look. Now let's look at the solution. This is a classic example of a chain reaction. Since x connects to y and y connects to 5, x is automatically connected to 5. Therefore, the correct answer is the transitive property of equality. Addition and multiplication are binary operations because they require two inputs to produce a third number. A set of numbers is said to be closed under a given operation if, when you perform that operation on any two members of the set, the result is also a member of that same set. The set of real numbers, R, is closed under both addition and multiplication. Adding and multiplying real numbers always produces other real numbers. Mathematically, if A and B belong to the real numbers, then a plus B and a times B must also belong to the real numbers. Imagine a magical island called the Real Number Island. No matter who you add or multiply inside this island, the result can never escape. It is trapped, meaning the final answer is always forced to stay on the same island. Let's look at a concrete example using real numbers. Take -3 and +5. Since both are real numbers, their sum, 2, is a real number. And their product, -15, is also a real number. This proves closure. Here is another practice problem. Consider the set of all odd numbers. Is the set of odd numbers closed under addition? Think about what happens when you choose any two odd numbers and add them together. Let's find out. Let's look at the answer. The correct choice is B. It is not closed. To prove this, we can find a counterexample. Let's take two odd numbers, 3 and 5. When we add 3 and 5, the result is 8. Since 8 is an even number, it escapes this set of odd numbers. Let's learn about the substitution principle, also known as the substitution property. For any real numbers A and B, the number A may be substituted for the number B if A equals B. This means that if two expressions have the same value, one expression can be written instead of the other. Let's look at some examples. For instance, the number 35 has the exact same value as 20 plus 15, or 30 plus 5. Therefore, 35 can be replaced by these expressions. Similarly, the expression 4 times 8 can be replaced with its exact value, 32. Think of the substitution principle like a money exchange at a store. A single $10 bill and two $5 bills look completely different. However, because their total value is exactly equal, you can freely substitute one for the other at the cash register. Let's test our understanding with a quiz. Evaluate the algebraic expression 3x plus 5, given that x is equal to 4. Use the substitution principle to find the final value. Let's see how it works. Here is the solution. By the substitution principle, since x equals 4, we can replace the variable x with the number 4. This turns the expression into 3 times 4 plus 5. 3 times 4 is 12, and 12 plus 5 gives us 17. In the real number system, 0 is the additive identity because adding it to any number does not change its value. Similarly, 1 is the multiplicative identity because multiplying any number by 1 leaves the number unchanged. Every real number has an additive inverse, which is its negative. When you add a number to its additive inverse, the result is always 0, the additive identity. For instance, the inverse of negative m is positive m. Think of identity elements as a magic mirror. No matter what number looks into it, the number stays exactly the same. In addition, 0 acts as this mirror because adding 0 leaves the number unchanged. In multiplication, 1 is the mirror because multiplying by 1 gives the exact same number. Now, think of the additive inverse as a perfect seesaw. Every number has an exact opposite partner that completely cancels it out, bringing the seesaw back to perfect balance, which is 0. For example, positive m and negative m cancel each other out to make 0. Let's test your understanding with a quick quiz. Find the unknown value x in the following equation. -7 plus x equals 0. Think about what property we should use here. Let's see how it works. Here is the solution. When we add a number to its additive inverse, the result is always 0, which is the additive identity. Since the given number is -7, its exact opposite partner is +7. Therefore, x must be equal to 7. Every non-zero real number has a multiplicative inverse, also known as a reciprocal. When you multiply a number by its multiplicative inverse, the result is always 1, which is the multiplicative identity. Let's look at the formal definition. However, there is an important exception to this rule. 0 has no reciprocal. Its reciprocal cannot be defined, which mathematically means that you can never divide any number by 0. Think of multiplication as drinking a magic potion that multiplies your size by m. To return to your original size of 1, you must drink its exact antidote, which is 1 over m. Multiplying a number by its reciprocal completely neutralizes the effect, bringing you back to 1. But what about 0? 0 acts like a mathematical black hole. Once you multiply any number by 0, it gets swallowed and crushed into 0. Because the original information is completely destroyed, there is no antidote or reciprocal that can ever bring it back. This is why you cannot divide by 0. Let's test our knowledge with a new quiz. Solve for y in the following equation. 2 over 3 times y equals 1. At the same time, think about what the reciprocal of 0 would be if it exists. Let's see the questions. Here is the solution. For question 1, when a number is multiplied by its reciprocal, the result is 1. The reciprocal of 2 over 3 is obtained by flipping the fraction, which gives us 3 over 2. For question 2, as we learned before, 0 has no reciprocal because you cannot divide by 0. Every real number can be found on the number line, whether it is rational or irrational. There is a perfect one-to-one correspondence between the real numbers and the points on the line. Every point represents exactly one real number. The numbers to the left of 0 are all negative, which means they are less than 0. The numbers to the right of 0 are positive, and they are greater than 0. Remember, 0 itself is neither negative nor positive. Think of the number line as a giant parking lot, where every single car represents a real number. Each car has one specific assigned parking slot, and no two cars can share the same space. This is what we call a one-to-one correspondence. Now, think of directions. If 0 is your starting point, walking east represents positive numbers, and walking west represents negative numbers. 0 itself is the center of the compass, so it doesn't face east or west. Let's test our understanding with a quiz. Consider the number line. Between which two consecutive integers can you find the negative real number negative 3.5? Think about its position relative to 0. Here is the solution. Since negative 3.5 is a negative number, we look to the left of 0. Moving left, negative 3.5 is less than negative 3, but greater than negative 4. Therefore, it lies exactly between negative 4 and negative 3. The absolute value of a number is its distance from 0 on the number line. Because distance is always positive or 0, absolute value ignores the sign and only measures the size. For example, both positive 4 and negative 4 have a distance of 4 from 0. More algebraically, the absolute value of C is defined in 3 parts. It is equal to C if C is positive, 0 if C is 0, and negative C if C is negative. Remember, negative C makes the value positive when C itself is already negative. Think of absolute value as a car's odometer. If you drive forward 4 miles, your odometer shows 4. If you drive backward 4 miles in reverse, the odometer still goes up by 4 miles, not negative 4. It only measures the total distance, completely ignoring the direction. What about the algebraic rule where the absolute value of negative C equals negative C? Think of it as a magic filter. If a positive number enters, it passes through untouched. But if a negative number enters, the filter multiplies it by another negative sign to cancel the minus, turning it back into a positive. Let's test your understanding with a quick quiz. Evaluate the following expression: the absolute value of negative 9 minus the absolute value of positive 5. Be careful with the operations outside the bars. Let's solve it. Here is the solution. First, evaluate each absolute value. The absolute value of negative 9 becomes positive 9, and the absolute value of 5 remains 5. Now, substitute these values back into the expression. 9 minus 5 gives us the final answer for. When you add two numbers with the same sign, the sum keeps that sign. Adding two positive numbers always results in a positive number. This means positive real numbers are closed under addition. Similarly, adding two negative numbers always gives a negative result, meaning negative numbers are also closed under addition. When adding numbers with opposite signs, the sign of the sum is determined by the addend with the larger absolute value. For instance, -5 plus 7 results in +2 because the absolute value of 7 is greater than -5. The larger size wins the sign. Think of addition as teams joining forces. When two positive numbers meet, they are in the same alliance, so they simply combine into a bigger positive team. They never leave their positive world, which means they are closed. The same goes for negative numbers. They combine into an even stronger negative team. What happens when opposite signs meet? It is like a tug of war. The positive team pulls one way, and the negative team pulls the other way. The final sign of the sum depends entirely on whichever team has more raw power, which represents the larger absolute value. The stronger side wins the sign. Let's test our understanding with a quiz. Evaluate the following addition expression: -12 plus 8. Pay close attention to which number has the larger absolute value before deciding the final sign. Let's solve it. Here is the solution. Since the two numbers have opposite signs, we must compare their absolute values. The absolute value of -12 is 12, which is greater than 8. Because the negative addend has the larger size, the final answer must be negative. 12 minus 8 gives us -4. When you multiply two real numbers, the sign of the product depends on the signs of the factors. Multiplying two numbers with the same sign always results in a positive product. However, multiplying two numbers with opposite signs gives a negative product. Let's look at the closure property. The set of positive real numbers is closed under multiplication because 5 times 2 equals +10. However, the set of negative real numbers is not closed under multiplication. Multiplying -5 and -2 results in +10, which leaks out of the negative set. Think of positive numbers as friends and negative numbers as enemies. The friend of my friend is my friend, so positive times positive is positive. More interestingly, the enemy of my enemy becomes my friend. This is why multiplying two negative numbers flips the result back to positive. Because the enemy of my enemy becomes a friend, the negative numbers cannot stay locked inside their own world. When two negatives multiply, they break through the wall and land in the positive world. That is why the set of negative numbers is not closed under multiplication. Let's test our understanding with a multiplication quiz. Evaluate the following expression: -4 times -6. After finding the answer, think about whether this result proves that negative real numbers are closed or not closed under multiplication. Let's look at the problem. Here is the solution. First, multiplying two negative numbers always results in a positive product. For times x is 24, so -4 times -6 gives us +24. Second, because the input factors were negative, but the output is positive, the result leaked out of the negative set. This directly proves that negative numbers are not closed under multiplication. Subtraction is the inverse operation of addition, defined as adding the opposite of a number. To subtract a from b, you simply add -a to b. Because subtraction is just a form of addition, and real numbers are closed under addition, they must also be closed under subtraction. However, subtraction has a key limitation. It is not commutative. This means that changing the order of the numbers changes the result. Therefore, b minus a is not equal to a minus b, except when both are equal. Think of subtraction as driving a car with a reverse gear. Instead of having a separate road for subtraction, we simply shift into reverse and push the gas pedal forward. Subtracting a is exactly the same as turning a into its opposite direction, negative a, and adding it to your position. Why is subtraction not commutative? Think of putting on your socks and shoes. Putting on socks first, then shoes, works perfectly. But if you try to put on shoes first, then socks, you get a completely different, messy result. Order matters in subtraction, so switching places changes everything. Let's test our understanding with a subtraction quiz. First, rewrite and evaluate the expression 3 minus negative 8 by adding the additive inverse. Second, calculate negative 8 minus 3 and determine if changing the order gives the same result. Let's see the questions. Here is the solution. For question 1, subtracting negative 8 is the same as adding its opposite, which is positive 8. 3 plus 8 gives us 11. For question 2, negative 8 minus 3 is rewritten as negative 8 plus negative 3, which equals negative 11. Since 11 is not equal to negative 11, this directly proves that subtraction is not commutative. Division is the inverse operation of multiplication, defined as multiplying by a reciprocal. To divide b by a, you simply multiply b by a inverse. The result of this division is called a quotient. Remember, the divisor can never be equal to 0. Just like subtraction, division is not commutative. Changing the order of the numbers completely changes the quotient. Therefore, a divided by b is not equal to b divided by a. Think of division as sharing a pizza. Dividing b by a is exactly the same as cutting the pizza into 1 over a size slices and then multiplying your portion by b. Dividing by a is simply multiplying by its upside-down partner, the reciprocal, 1 over a. Why is division not commutative? Imagine 6 pizzas shared among 2 people. Everyone gets 3 full pizzas. But if you switch the order, 2 pizzas shared among 6 people means everyone only gets a tiny fraction, 1/3 of a pizza. Who divides whom completely changes the result. Let's test our understanding with a division quiz. First, rewrite and evaluate the expression 4 divided by 2 over 3 by multiplying the reciprocal. Second, calculate 2 over 3 divided by 4 and check if switching the order changes the quotient. Let's look at the problems. Here is the solution. For question 1, dividing by 2 over 3 is the same as multiplying by its reciprocal, which is 3 over 2. 4 times 3 over 2 gives us 6. For question 2, 2 over 3 divided by 4 is rewritten as 2 over 3 times 1 over 4, which equals 1 over 6. Since 6 is not equal to 1 over 6, division is not commutative. If you want to write an expression 4, add 5 and 4, then multiply the answer by 3. Writing 5 plus 4 times 3 causes confusion. Depending on what you do first, you get completely different answers, 27 or 17. To make the calculation clear, we use grouping symbols. By putting parentheses around 5 plus 4, anyone can see that addition must be done first. This gives us the unique and correct answer, 27. Now, let's test what we've learned with a quick quiz. Look at these two expressions. They have the exact same numbers, but the grouping symbols are in different places. Evaluate both expressions and see how the parenthesized group changes the final answer. Let's look at the solutions. For question 1, the parentheses tell us to add 6 and 4 first, which gives us 10. Then, multiplying 2 by 10 gives 20. For question 2, there are no parentheses, so we follow the standard order of operations and multiply 2 by 6 first to get 12. Adding 4 gives us 16. As you can see, parentheses change the order, and the order matters. There are specific rules about what to evaluate first. This order of operations is used by all mathematicians so that every mathematician in the world evaluates expressions in the same way. Let's break down the 4 rules. First, calculate expressions within grouping symbols from the innermost to the outermost. Second, calculate expressions involving exponents. Third, do all multiplication and division from left to right. Lastly, do any addition or subtraction, also from left to right. Let's imagine a huge music concert. Think of mathematical operations as people waiting to enter the concert hall. Some people have special passes to get in first. First, grouping symbols are the VIP guests hidden inside private lounges. They go first. Second, exponents are the VIP ticket holders who cut the main line. Third, multiplication and division are regular ticket holders standing side by side. Lastly, addition and subtraction are the economy pass holders who must wait. Now let's test your skills with a challenge. Evaluate this expression using our concert rules. Remember who gets the VIP access first. Pause the video if you need a moment to solve it yourself. Let's solve it together. Step 1, we have grouping symbols. The VIP lounge guests inside the parentheses go first, so 2 plus 4 gives 6. Step 2, we multiply 3 by 6 to get 18. Finally, step 3, we subtract 5 from 18. Our final answer is 13. Great job! Today, we are learning about commutative laws. It means the order doesn't matter. For addition, a plus b is equal to b plus a. The same is true for multiplication. A times b equals b times a. As you can see in the examples, 2 plus 3 equals 3 plus 2. Let's visualize this with a simple analogy. Imagine putting fruits into a basket. If you put 2 red apples first and then 3 green apples, or if you put 3 green apples first and then 2 red apples, the total amount of fruits in the basket is exactly the same. The switching of the order changed nothing. Now let's test your understanding of the commutative law. Look at this multiplication expression. 4 times 7 equals 28. Based on the commutative property, fill in the blank to complete the equation. Think about how the numbers swap their places. Let's solve it together. The commutative property states that for multiplication, the order of the numbers does not change the final result. Since 4 times 7 equals 28, swapping the order tells us that 7 times 4 must also equal 28. Therefore, The missing number in the blank is 7. Excellent job. Next, we have the associative laws. Addition and multiplication are binary operations, meaning we can only group two numbers at a time. However, it doesn't matter which two you group first. For addition, open parenthesis a plus b close parenthesis plus c equals a plus open parenthesis b plus c close parenthesis. The same logic applies to multiplication as well. Let's visualize this with a train analogy. Imagine connecting three separate train cars, red, green, and blue. In case 1, you connect the red and green cars first, then attach the blue car. In case 2, you couple the green and blue cars first, then connect the red car at the front. Look at the final result. Either way, you get the exact same long train. How you group them makes no difference. Now, let's test your understanding of the associative law with a challenge. Look at this expression, open parenthesis 47 plus 25 close parenthesis plus 75. Adding 47 and 25 first might be tricky. Use the associative property to regroup the numbers and make this calculation much easier. Pause the video and try it yourself. Let's solve it together. According to the associative law, we can group numbers any way we want. Instead of adding 47 and 25 first, we can move the parentheses to group 25 and 75 together. 25 plus 75 gives us a clean 100. Finally, adding 47 to 100 gives our final answer, 147. See how much easier that was? Finally, we have the distributive laws. This law defines how multiplication and addition combine together. When you multiply a factor outside by a sum inside the parentheses, it multiplies every single term inside. Therefore, a times open parenthesis b plus c close parenthesis equals a times b plus a times c. Let's visualize this with a gift delivery analogy. Imagine a house containing one person inside a circle room and another inside a triangle room. A delivery manager, represented by the square outside, brings special items. The manager outside must deliver the item to every single person inside the house. So, the circle person gets an item and the triangle person also gets an item. Everyone gets a share equally. Now, let's test your skills with the distributive law challenge. Evaluate this expression. 6 times open parenthesis 10 plus 2 close parenthesis. Instead of calculating inside the parentheses first, apply the distributive property to multiply 6 out to both terms inside. Pause the video and try it now. Let's solve it step by step. The distributive law tells us that the factor outside multiplies every term inside the house. Step 1, we multiply 6 by 10, which gives 60. Step 2, we multiply 6 by 2, which gives 12. Finally, step 3, we add 60 and 12 together. Our final answer is 72. Fantastic job! Welcome back. In Chapter 1, we explore working with real numbers. So far, we have covered sets and expressions in Section 1.1 and examined the structure of the real number system in Section 1.2. Now, it's time to transition to our next critical topic. Today, we dive deeply into Section 1.3, focusing on exponents, roots, and fractions. We will master how powers scale numbers, how radicals unlock roots, and how fractions partition values. Let's get started. A power is a multiplication in which all the factors are the same. For example, m squared equals m times m, and m cubed equals m times m times m. In this expression, m is called the base, and the number above is called the exponent. Imagine Santa Claus multiplying his magic gift boxes. If he doubles them at each house, 2 squared becomes 4, and 2 cubed rapidly scales to 8. That is the explosive speed of repeated multiplications. Let's mathematically derive the multiplication of exponents. When we multiply m squared by m cubed, we expand them into repeated factors. M squared is m times m, and m cubed is m times m times m. Count them all together, and we get m multiplied 5 times, which equals m to the 5th power. Thus, when multiplying powers with the same base, we simply add the exponents. Next, let's explore division. Consider m to the 5th power divided by m squared. We can write this as a fraction, with 5 m's multiplied in the numerator and 2 m's multiplied in the denominator. By canceling out 2 matching factors from both top and bottom, we are left with exactly 3 m's. This gives us m cubed. Therefore, for division, we subtract the exponents. Now, let's test your understanding with a practice problem. Simplify the following expression, m to the 4th power multiplied by m cubed and then divided by m squared. Think about which rules to apply first. Let's solve this step by step. First, look at the numerator. According to the product rule, m to the 4th times m cubed equals m to the 4 plus 3 power, which simplifies to m to the 7th power. Next, we apply the quotient rule for the division. M to the 7th divided by m squared equals m to the 7 minus 2 power. This gives us our final simplified answer, m to the 5th power. Rule number 3. When you raise a power to a power, you multiply the exponents. For example, let's take m cubed and square the entire expression. This means we multiply m cubed by itself. By expanding each term, we get m times m, multiplied by another m times m. Count them up, and we get m multiplied 6 times, which is m to the 6th power. We can find this directly by multiplying the exponents 3 and 2. Rule number 4. Raising a product or quotient to a power is the same as raising each of its individual elements to that power. For example, let's look at the product m times b raised to the 3rd power. This expands to mb times mb times mb. By grouping the like terms together, we get m times m multiplied by b times b. This simplifies neatly to m cubed, b cubed. The same logic applies to fractions, distributing the exponent to both top and bottom. Let's check your skills with a challenging practice problem. Simplify the following expression. Inside the parentheses, m squared times b squared, and raise the entire expression to the 3rd power. Think about how to distribute the exponent to each element inside. Let's break this down step by step. First, according to the product to a power rule, we must distribute the outside exponent 3 to both individual elements inside the parentheses. This gives us m squared raised to the 3rd power, multiplied by b squared raised to the 3rd power. Next, we apply the power to a power rule. For m, we multiply the exponents 2 and 3, resulting in m to the 6th. For b, we also multiply 2 and 3, resulting in b to the 6th. Our final simplified answer is m to the 6th power times b to the 6th power. Rule number 5. Let's understand why any non-zero number raised to the power of 0 equals 1. Using the product rule, we know that m to the power of a multiplied by m to the power of 0 equals m to the power of a plus 0. Since a plus 0 is just a, the result is simply m to the power of a. Notice that multiplying by m to the power of 0 did not change the original value at all. Therefore, m to the power of 0 must equal 1. Rule number 6. Now, let's make sense of a negative exponent. Consider m to the power of a multiplied by m to the power of negative a. According to the product rule, we add the exponents, giving us m to the power of a minus a. This simplifies to m to the power of 0, which we already proved equals 1. Because their product is 1, m to the power of negative a is the reciprocal of m to the power of a. Thus, m to the power of negative a equals 1 divided by m to the power of a. Let's put your knowledge to the test with another practice problem. Evaluate and simplify the following expression, m to the negative third power, multiplied by m to the power of 0, and then multiplied by m to the fifth power. Think about how to combine these different exponent types. Let's solve this efficiently. We can approach this in two ways. First, remember that m to the power of 0 equals 1. Multiplying by 1 doesn't change anything, so we can focus on the remaining terms. Now, apply the product rule by adding the exponents, negative 3 and 5. Negative 3 plus 5 equals 2. This gives us our final simplified result, m squared. Rule number 7 introduces fractional powers. Taking a root can be written using a fraction in the exponent. To understand why, remember the definition of the nth root of a. By definition, the nth root of a is a number that, when raised to the nth power, becomes exactly a. Keep this fundamental relationship in mind as we begin our proof. Now, let's mathematically prove why these two expressions are equal. Let's assume the nth root of a can be written as a to the power of an unknown variable, x. To solve for x, we raise both sides of the equation to the nth power. On the left side, the nth power cancels the root, leaving just a, or a to the first power. On the right side, applying the power to a power rule, we multiply the exponents, getting a to the nx power. Since the bases are identical, their exponents must be equal. Therefore, 1 equals n times x. Dividing both sides by n, we find that x must equal 1 over n. This perfectly proves that the nth root of a is exactly equal to a to the 1 over n power. Let's practice what we just learned with a real problem. Simplify the following expression, the cube root of 8 raised to the second power. Think about how to rewrite the cube root into a fractional power form first. Let's break it down together. First, we know that the number 8 can be written as 2 cubed. Next, rewrite the cube root using a fractional power. The cube root becomes a power of 1 over 3. By applying the power to a power rule, we multiply the inner exponents, 3 times 1 over 3. They cancel out completely, leaving just 2 inside the parentheses. Finally, we square that result. 2 to the second power equals 4. So, our final answer is 4. Another name for the root sign is the radical sign. The square root of p is written with this symbol, and multiplying it by itself gives us p. In the expression of the nth root of p, the symbol itself is called the radical sign, and the value inside, p, is called the radicand. This radical sign always represents the non-negative root when multiple roots exist. For any real number p greater than 0, squaring either r or negative r results in p. Here, the positive result, r, is called the principal square root of p. On the other hand, the negative result, negative r, is called the minor square root of p. Remember that the radical symbol by itself always denotes the principal, non-negative root. Let's check your understanding with a comprehensive problem. Identify the radicand of the expression, the fourth root of 16. Then, find both its principal square root and its minor square root. Let's break down the solution. First, the value inside the radical sign is 16, so the radicand is 16. Next, we look for a number that equals 16 when multiplied 4 times, which is 2. Therefore, the positive result, 2, is the principal square root, and the negative result, negative 2, is the minor square root. Both values satisfy the core definition of the radical relationship. In practice, this means that every positive number always has 2 square roots. One is a positive value, which we call the principal square root. The other is a negative value, known as the minor square root. Squaring either of these 2 roots will always result in the original positive number. Let's look at this concept through a mirror reflection analogy. Imagine a target number inside a special room. Both a real object and its opposite reflection in the mirror cast the exact same shadow when squared. The squaring process acts like a filter that hides the original sign, revealing 2 opposite paths leading back to a single source. Now, let's look at a practice quiz to test your skills. Find both square roots of 49 and clearly state which one is the minor root. Think about how the dual nature of roots applies to this positive integer value. Let's break down the solution step by step. We know that 7 squared equals 49, making positive 7 the principal square root. At the same time, negative 7 squared also equals 49. Therefore, negative 7 is the minor square root. The final answers are positive 7 and negative 7. Let's explore the multiplicative property of square roots. The property states that the square root of mc is exactly equal to the square root of m multiplied by the square root of c. This rule allows us to simplify complex radical expressions by factoring the radicand first. Now, let's mathematically prove why this property holds true. First, remember that any square root can be rewritten as a fractional power of 1 over 2. Therefore, the square root of mc becomes the expression mc raised to the half power. According to the laws of exponents, we can distribute this power of 1 over 2 to each factor inside. This gives us m to the half power, multiplied by c to the half power. Finally, convert these fractional exponents back into radical signs. This beautifully results in the square root of m times the square root of c, completing our proof. A factor of a number is a number that divides into it without a remainder. For example, 1, 2, 3, 6, 9, and 18 are factors of 18. To factor a number means to write it as a product of its factors, such as 18 equals 9 times 2. Factoring is an essential step when simplifying square roots. Now let's solve a practice problem using this concept. Let's simplify the square root of 18. First, we split 18 into its factors, choosing a perfect square, 9 times 2. Next, we split the radical into the square root of 9 multiplied by the square root of 2. Since the square root of 9 simplifies perfectly to 3, our final simplified answer is 3 times the square root of 2. Let's mathematically prove the division property of square roots. Any square root can be expressed as a fractional power of 1 over 2. Therefore, the square root of m over c can be written as the fraction m over c raised to the half power. According to the rules of exponents, we distribute the power of 1 over 2 to both the numerator and the denominator. This gives us m to the half power over c to the half power. Finally, converting these fractional exponents back into radical symbols, we neatly get the square root of m divided by the square root of c. Now let's apply this property to a practice quiz. Let's simplify the square root of 3 over 16. First, according to our division property, we split the radical into the numerator and the denominator. This gives us the square root of 3 divided by the square root of 16. Since 16 is a perfect square, its square root simplifies perfectly to 4. Therefore, our final simplified answer is the square root of 3 over 4. A fraction is any number expressed as one integer divided by another integer. Fractions are written in the form of p over q, where p and q are integers and q cannot be 0. The top number, p, is called the numerator, and the bottom number, q, is called the denominator. A fraction with a denominator of 0 is undefined because you cannot divide by 0. Equivalent fractions are fractions that express the exact same value. For example, 3 over 4 is equal to 6 over 8, and 1 over 3 has the same value as 3 over 9. To simplify 6 over 8 to 3 over 4, you can rewrite the numerator and denominator as products of factors. Then, you can cancel out the common factor, 2, by dividing both parts to produce the equivalent irreducible fraction. Let's check your skills with a practice quiz. Simplify the given fraction, 12 over 15, into its simplest equivalent form. Think about finding the greatest common factor for both the numerator and the denominator. Let's solve this efficiently. First, we find that both 12 and 15 can be divided by their greatest common factor, which is 3. We rewrite 12 as 4 times 3 and 15 as 5 times 3. By canceling out the common factor of 3 from both the top and the bottom, we produce the final simplified equivalent fraction for over 5. To multiply two fractions, we find the product of the numerators and divide that by the product of the denominators. In other words, simply multiply the top numbers together and multiply the bottom numbers together. Now let's look at a practice quiz. Let's multiply 2 over 3 by 5 over 7. First, we find the product of the numerators by multiplying 2 and 5, which gives us 10. Next, we find the product of the denominators by multiplying 3 and 7, which equals 21. Combining these two parts together, our final simplified answer is 10 over 21. You should always give your answer in its simplest form. With more complicated examples, factor the numerators and denominators and cancel common factors. It will save a lot of time if you do this before you compute the products. Let's practice with a useful example. Multiply 3 over 8 by 4 over 9. Instead of multiplying straight across to get large numbers, let's factor first. Notice that 4 and 8 share a common factor of 4, and 3 and 9 share a common factor of 3. By canceling out these common factors before computing, the expression beautifully reduces. We are left with 1 times 1 on top and 2 times 3 on the bottom. Our final simplified answer is 1 over 6. The reciprocal of a fraction c over d is d over c, since their product equals 1. To divide by a fraction, you simply multiply by its reciprocal. This rule allows us to change any complex fraction division into a simple multiplication task. Let's practice with an example. Divide 2 over 3 by 5 over 4. According to the rule, we change the division into a multiplication by flipping 5 over 4 into its reciprocal for over 5. Now multiply the top numbers 2 and 4 to get 8. Then multiply the bottom numbers 3 and 5 to get 15. Our final simplified result is 8 over 15. To find the sum or the difference of two fractions with the same denominator, just add or subtract the numerators, then divide by the common denominator. Keep the bottom number exactly as it is, and only perform the math on the top numbers. Let's think about this using a pizza analogy. The denominator tells you how many slices make up a whole pizza pie. If you have one slice out of 8, and add 3 more slices out of the same 8, the size of each slice does not change. You simply have 1 plus 3, which equals 4 slices out of 8 in total. Now let's solve a practice problem. Let's calculate 1 over 7 plus 4 over 7. Since the denominators are both 7, we keep the common denominator fixed on the bottom. Next, we add the numerators on top, 1 plus 4, which gives us 5. Our final simplified answer is 5 over 7. To add fractions with different denominators, we first convert them into equivalent fractions with the same denominator. This common denominator must be the least common multiple, or LCM, of the two denominators. The LCM is the smallest possible number that is perfectly divisible by both numbers. Let's visualize this using chocolate bars with different grid sizes. Imagine one bar split into 2 large pieces and another bar split into 3 medium pieces. You cannot easily add 1/2 and 1/3 because their slice sizes are totally different. To solve this, we draw a new grid, cutting both bars into 6 tiny equal blocks. Now, 1/2 becomes 3 blocks and 1/3 becomes 2 blocks. With the exact same block sizes, we can finally add them together to get 5 blocks out of 6. Let's put your skills to the test with a practice quiz. Calculate and simplify the sum of 1 over 4 and 2 over 3. Remember to find the least common multiple of the denominators first. Let's solve it together. The denominators are 4 and 3, and their least common multiple is 12. We convert 1 over 4 by multiplying the top and bottom by 3, making it 3 over 12. We convert 2 over 3 by multiplying the top and bottom by 4, making it 8 over 12. Now that they share a common denominator, we simply add the numerators, 3 plus 8. This gives us our final answer, 11 over 12. Welcome to Chapter 2. In this unit, we explore single variable linear equations. Today, we officially begin our journey with Section 2.1, focusing on algebra basics. Let's dive into the core foundations of algebraic expressions. In Section 2.1, we will master how to identify variables, coefficients, and constants. Understanding these basics is essential before we solve complex linear equations. Let's get started. Algebraic expressions are made up of individual building blocks called terms. A term can be a product of numbers and variables, or just a single number. These terms are separated by plus and minus signs. Crucially, each sign always belongs to the specific term directly in front of it. The very first term has an invisible positive sign. To visualize this perfectly, think of an algebraic expression as a long freight train. Each individual car represents a single mathematical term. The plus and minus signs act as the heavy couplers linking the cars together. Just like a real train, each coupler is permanently welded to the front of the car behind it. Wherever that cargo car travels, its sign moves with it as a single unit. Let's test your skills with a new practice quiz. For the given expression, determine the total number of terms. Then identify the exact mathematical value of the third term, including its sign. Let's break down the solution. By counting each element separated by the signs, we find a total of 4 terms. Next, we look at the third group in the expression. Remembering that the minus sign belongs permanently to the term following it, the value of the third term is exactly negative 8x. Let's put your skills to the test with an application problem. Simplify the following algebraic expression: 6x squared minus 2x plus 4x squared minus 5x plus 8. Think about how to group the like terms together before computing. Let's solve this step by step. First, we rearrange the terms by grouping the like terms together using the commutative property. This gives us 6x squared plus 4x squared, followed by minus 2x minus 5x and plus 8. Next, combine the coefficients of the x squared terms, which yields 10x squared. Then, combine the coefficients of the x terms, resulting in negative 7x. Our final simplified expression is 10x squared minus 7x plus 8. To simplify an algebraic expression with grouping symbols, you must first remove them. We achieve this by applying the distributive property of multiplication over addition. When a factor is placed outside the parentheses, it multiplies every single term inside, transforming a times the quantity b plus c into ab plus ac. Let's check your skills with a practical problem. Simplify the following algebraic expression by removing the grouping symbols. For times the quantity 2x plus 3. Think about how the outside factor distributes to each term inside. Let's solve this efficiently step by step. First, distribute the outside factor 4 to the first term inside, which is 2x. For times, 2x yields 8x. Next, distribute the 4 to the second term inside, which is positive 3. For times, 3 results in 12. Combining these elements, our final expanded expression is 8x plus 12. Take extra care when the number outside the grouping symbol is negative. When distributing a negative value, you must use the multiplicative property of -1. This means the signs of all terms inside the parentheses will completely reverse. Positive signs change to minus signs, and minus signs change to positive signs. To multiply variables, you must combine the distributive property with exponent rules. When expanding complex expressions, remove the grouping symbols first by distributing the outside term. Remember that x times x squared equals x cubed. Also, order does not matter when multiplying different variables because of the commutative property. xy is completely identical to yx. Let's practice what we just learned with a real challenge. Simplify the given algebraic expression, minus 3x times the quantity x minus 2y. Think about combining the exponents and reversing the internal signs carefully. Let's break down the solution step by step. First, distribute minus 3x to the first term inside, which is x, minus 3x times x yields minus 3x squared. Next, distribute minus 3x to the second term inside, which is minus 2y. A negative times a negative becomes positive, resulting in positive 6xy. Our final simplified answer is minus 3x squared plus 6xy. Equations can contain two or more different variables at the same time. To prove that both sides of an equation are equal, substitute the given numbers into each variable. Then, simplify step by step using the standard order of operations. By calculating both the left and right sides independently, we can successfully show that the final values match perfectly. In this chapter, we are exploring single variable linear equations. Today, we will focus specifically on Section 2.2, Manipulating Equations, and Section 2.3, More Equations. Let's master these core concepts together. An equation states that two expressions have the same value. The expression on the left is the left-hand side, and the expression on the right is the right-hand side. When variables are included, the value that satisfies the equation is called the solution. Think of an equation as a perfectly balanced scale. The equal sign represents the center pivot. To keep the scale perfectly horizontal and balanced, the mathematical weights on both sides must always be exactly identical. To solve equations, we use the properties of equality. The addition property states that if A equals B, then adding C to both sides maintains the equality. Similarly, the subtraction property states that subtracting C from both sides gives an equivalent equation. These operations allow us to isolate the variable and solve the equation. Let's visualize this with a simple scale. Imagine two identical mystery boxes that have the exact same weight. If we add the same amount of sweet candy to both sides at the same time, the scale remains perfectly horizontal. Even if we take away the same number of candies later, the perfect balance never breaks. Let's test our understanding with a practice problem. Solve the equation x minus 6 equals 13. To isolate the variable x, we apply the addition property of equality. By adding 6 to both sides of the equals sign, the balance is perfectly kept, and we successfully find that our solution is x equals 19. Next, we have the multiplication and division properties of equality. The multiplication property states that multiplying both sides of an equation by the same number C keeps the equation balanced. Similarly, the division property states that you can divide both sides by any non-zero number C. Just like addition and subtraction, these operations help you isolate the variable perfectly. Let's check the multiplication and division property with shapes. Here is a balanced scale with one mystery box on each side. If we multiply the left side by 2, we double the number of boxes. To keep the scale perfectly level, we must also double the right side instantly. The same rule applies when dividing. Cutting both sides exactly in half maintains the balance. Let's test what we have learned with another practice problem. Solve the equation 4x equals 32. To completely isolate the variable x, we must use the division property of equality. By dividing both sides of the equation by 4 at the same time, the perfect level balance is kept. Simplifying this calculation leads us to our final answer, x equals 8. To solve equations with fractional coefficients, we can clear the fractions to make things easier. We do this by multiplying both sides of the equation by a common multiple of the denominators. The most efficient number to multiply by is the least common multiple, or LCM. Let's look at this equation with denominators 3 and 5. By finding their LCM, which is 15, we can transform this into a much simpler integer equation. Let's visualize clearing fractions using cake slices. Dealing with sliced pieces of cake on a scale can be complicated. However, if we use a magic number to multiply the slices on both sides, those broken pieces instantly combine into beautiful whole cakes. Multiplying by the least common multiple changes messy fractions into clean integers. Let's test our skills with a comprehensive problem. Solve the equation 1/3 x minus 2 equals 1/5 x. To clear the denominators 3 and 5, we multiply every single term by their LCM, which is 15. This converts the equation into 5x minus 30 equals 3x. By rearranging the terms step by step, we get 2x equals 30. Finally, dividing by 2 leads us to the answer, x equals 15. Let's solve a similar advanced problem together. Consider the equation x minus 1 over 3 minus x minus 2 over 4 equals 5 over 12. We have 3 different denominators, 3, 4, and 12. Their least common multiple is 12. By multiplying every single term by 12, we can perfectly clear the fractional coefficients. This leaves us with 4 times the quantity x minus 1 minus 3 times the quantity x minus 2 equals 5. After opening the brackets carefully using the distributive property, we group the terms step by step and successfully find that our final answer is x equals 3. When an equation contains decimals, we can clear them by multiplying a power of 10. Let's look at this equation. The numbers have up to 2 decimal places, which means hundredths. Therefore, we multiply both sides of the equation by 100. By doing this, every single decimal term is converted into clean integers. Then we rearrange the terms, group the variables, and solve it cleanly without any fractions. Let's tackle a similar advanced problem involving thousandths. Solve the equation 0.012x equals 0.3 minus 0.018x. Since the numbers contain up to 3 decimal places, we multiply both sides by 1,000 this time. This step clears the decimals, yielding the integer equation 15x equals 300 minus 25x. Next, we move the variable term by adding 25x to both sides, which simplifies perfectly to 40x equals 300. Finally, dividing both sides by 40 brings us to the verified solution, x equals 10. Let's learn how to translate real-life word problems into equations. Consider this task. The sum of 3 times a number y and 5 is 26. First, we identify our variable, which is already labeled as y. Next, we write out the given information as an algebraic equation, yielding 3y plus 5 equals 26. To solve it, we isolate the variable term by subtracting 5 from both sides, which gives 3y equals 21. Finally, dividing both sides by 3 brings us to the final solution, y equals 7. Let's explore sequences with a common difference. Consecutive even integers always increase by a fixed amount of 2. Imagine we need to find 3 consecutive even integers whose sum is exactly 72. We can visually represent them as x, x plus 2, and x plus 4. Adding them together gives the equation x plus 2 plus x plus 4 equals 72. By combining the like terms, this simplifies beautifully to 3x plus 6 equals 72. Subtracting 6 from both sides gives 3x equals 66. Finally, dividing by 3 shows that the first integer x equals 22. So, our 3 consecutive even integers are 22, 24, and 26. Speed, time, and distance are all connected by a simple mathematical relationship. Speed is defined as the distance traveled per unit of time. We can visually arrange these variables into a formula triangle. Distance stays on top, while speed and time occupy the bottom positions. By rearranging this triangle, we discover that distance equals speed multiplied by time. Let's test this concept with a practical practice problem. A train travels at a steady speed of 65 miles per hour for exactly 4 hours. To calculate the total distance covered, we multiply the speed of 65 by the time of 4. This gives us the final equation. 65 times 4 equals 260. Therefore, the verified total distance is 260 miles. An absolute value represents the distance from 0 on a number line. When an absolute value contains multiple terms, we must keep them together. Let's solve the equation. The absolute value of 3x minus 4 equals 8. This means the expression inside 3x minus 4 can be either positive 8 or negative 8. We split this into 2 separate cases to solve. For the first case, 3x minus 4 equals 8. Adding 4 gives 3x equals 12, so x equals 4. For the second case, 3x minus 4 equals negative 8. Adding 4 gives 3x equals negative 4, which simplifies to x equals negative 4/3. Both answers are verified and correct solutions. Welcome back. In this video, we are going to explore Chapter 3, Single Variable Linear Inequalities. Throughout this chapter, we will cover 4 essential sections. First, Section 3.1 introduces the core concept of inequalities. Next, Section 3.2 explores the practical applications of inequalities. After that, Section 3.3 focuses on solving compound inequalities. Finally, Section 3.4 guides us through absolute value inequalities. Let's dive into Chapter 3 together and master these core concepts. An inequality is a mathematical sentence that states that two expressions are not equal. We use 4 core symbols to represent these relationships: the less than symbol, the greater than symbol, the less than or equal to symbol, and the greater than or equal to symbol. For example, we read the expression y is greater than or equal to 5 to show that y can be 5 or any number bigger than 5. Now let's show an inequality on the number line. Our problem is to graph x is greater than 3. This represents the interval where numbers are strictly greater than 3. To draw this, we place an open circle at the endpoint 3. The circle is open because 3 is excluded from the solution. Then we draw a bold arrow pointing to the right. In interval notation, this open interval is written as 3 to infinity. The addition property of inequalities states that if we add the same number to both sides of an inequality, it gives an equivalent inequality. Given real numbers a, b, and c, if a is greater than b, then a plus c is greater than b plus c. Let's apply this to example 1. Solve and graph the solution of x minus 4 is greater than 2 on a number line, and write the solution in interval notation. To solve, we start with x minus 4 is greater than 2. Using the addition property, we add 4 to both sides. This simplifies beautifully to x is greater than 6. Now let's look at the graph. We place an open circle at 6 because 6 is not included, and draw a bold arrow to the right. Finally, the solution in interval notation is written as open interval 6 to infinity. The subtraction property of inequalities states that if we subtract the same number from both sides of an inequality, it gives an equivalent inequality. Given real numbers a, b, and c, if a is greater than b, then a minus c is greater than b minus c. Let's solve example 2. Solve and graph the solution of 4x is less than or equal to 8 plus 3x on a number line. Write the solution in interval notation and state the maximum integer value of x that satisfies this relationship. To solve, we subtract 3x from both sides. This simplifies directly to x is less than or equal to 8. For the graph, we place a solid closed circle at 8 because 8 is included in our solution, and draw a bold arrow pointing to the left. In interval notation, this is negative infinity to 8 with a bracket. Therefore, the maximum integer value of x is exactly 8. The multiplication property of inequalities states that if we multiply both sides of an inequality by a positive number, it gives an equivalent inequality. Given real numbers a, b, and c, if A is greater than B and C is greater than 0, then A times C is greater than B times C. Notice that the direction of the inequality stays the same. Let's look at example 1. Solve the inequality. 1/3 of x is greater than 4 and graph the solution on a number line. To clear the fraction and isolate x, we use the multiplication property. We multiply both sides of the inequality by +3. Since 3 is positive, the inequality sign remains the same. This simplifies perfectly to x is greater than 12. On the number line, we place an open circle at 12 because 12 is excluded and draw a bold arrow to the right. The final solution in interval notation is written as open interval 12 to infinity. The division property of inequalities states that if we divide both sides of an inequality by a positive number, it gives an equivalent inequality. Given real numbers A, B, and C, if A is greater than B and C is greater than 0, then A over C is greater than B over C. Just like multiplication, dividing by a positive number keeps the inequality sign in the same direction. Now let's tackle example 2. Solve the inequality for x is greater than 15 and graph the solution on a number line. To isolate x, we apply the division property and divide both sides by +4. Since 4 is a positive number, the direction of the inequality remains exactly the same. This simplifies to x is greater than 15/4. 15/4 is equal to 3.75. On the number line, we place an open circle at 15/4 because this point is excluded and draw a bold arrow pointing to the right. The solution in interval notation is written as open interval 15/4 to infinity. This is really important, so make sure you listen carefully. When we multiply both sides of an inequality by a negative number, the relationship reverses. Given real numbers A, B, and C, if A is greater than B and C is less than 0, then A times C is less than B times C. Remember, you must reverse the inequality symbol, otherwise the statement will be false. Let's solve example 3. Solve the inequality. -1/3 of x is greater than 3 and graph the solution on a number line. To isolate x, we need to clear the fraction by multiplying both sides by -3. Because we are multiplying by a negative number, we must reverse the inequality symbol. The greater than sign flips to a less than sign. This simplifies beautifully to x is less than -9. On the number line, we place an open circle at -9 because -9 is excluded and draw a bold arrow pointing to the left. The final solution in interval notation is written as -infinity to -9. Just like multiplication, the division property with negative numbers is crucial. If you divide both sides of an inequality by a negative number, you have to reverse the inequality symbol, otherwise the statement will be false. Given real numbers A, B, and C, if A is greater than B and C is less than 0, then A over C becomes less than B over C. Now let's look at example 4. Solve the inequality. -7x is less than or equal to 28 and graph the solution. To isolate x, we divide both sides by -7. Since we are dividing by a negative number, we must reverse the inequality symbol. The less than or equal to sign flips to a greater than or equal to sign. This simplifies beautifully to x is greater than or equal to -4. On the number line, we place a solid closed circle at -4 because it is included, and draw a bold arrow pointing to the right. The final solution in interval notation is written as bracket -4 to infinity. To solve multi-step inequalities, we combine several techniques. Our main goal is to isolate the terms with x on one side and isolate the numbers on the other. It is often easiest to keep the x terms on the side where they will have a positive value, so we can avoid dealing with negative coefficients later. Let's look at example 1. Solve the inequality 5x minus 9 is greater than 2x, and graph the solution on a number line. First, let's eliminate -9 from the left side by adding 9 to both sides. This gives 5x is greater than 2x plus 9. Next, we move the 2x term to the left side by subtracting 2x from both sides. This simplifies beautifully to 3x is greater than 9. Finally, divide both sides by 3 to isolate x. The solution is x is greater than 3. On the number line, we place an open circle at 3 and draw a bold arrow to the right. In interval notation, this open interval is written as 3 to infinity. When tackling more complicated inequality questions, we can break them down into easier steps using a useful checklist. First, multiply out any parentheses. Second, simplify each side of the inequality. Third, remove number terms from one side. Fourth, remove x terms from the other side. And finally, multiply or divide to get an x coefficient of 1. Let's apply this checklist to example 2. Solve the inequality 5 times x minus 2 minus 2 times x minus 5 is greater than 2 times x minus 4. Step 1. Multiply out the parentheses using the distributive property. This gives 5x minus 10 minus 2x plus 10 is greater than 2x minus 8. Step 2. Simplify the left side by combining like terms. -10 and +10 cancel out, and 5x minus 2x leaves us with 3x. So, 3x is greater than 2x minus 8. Step 3. Remove the 2x term from the right side by subtracting 2x from both sides. This simplifies neatly to x is greater than -8. Our coefficient is already 1. On the number line, we place an open circle at -8 and draw a bold arrow to the right. The interval notation is written as open interval -8 to infinity. Today we are going to learn about solving conjunctions. The solution to a conjunction must satisfy both inequalities. This means that both individual inequalities must be true at the same time. Let's solve example 1. Solve and graph the inequality. -5 is less than 3x plus 1, which is less than 7. Our main aim is to isolate x all by itself in the middle. First, let's subtract 1 from all three parts of the inequality. This gives -6 is less than 3x, which is less than 6. Next, to get x completely by itself, we divide all parts by +3. This simplifies beautifully to -2 is less than x, which is less than 2. So, our solution is any number greater than -2, but less than +2. Let's look at the graph. We place open circles at both endpoints, -2 and 2, and draw a bold red line connecting them in the middle. Now let's talk about solving disjunctions. Disjunction problems always include the word or. The solution to a disjunction is all the numbers that satisfy either one inequality or the other. Let's look at example 2. Solve and graph the solution set of 2x minus 5 is less than negative 3, or 2x minus 5 is greater than 3. To solve, we handle both inequalities. First, let's add 5 to both sides of both inequalities. On the left, it simplifies to 2x is less than 2. On the right, it becomes 2x is greater than 8. Next, we divide both sides of both inequalities by positive 2. This gives x is less than 1 or x is greater than 4. This means our solution includes any number smaller than 1 or any number larger than 4. Let's check the graph. We place open circles at 1 and 4. From 1, we draw a bold arrow to the left, and from 4, we draw a bold arrow to the right. Absolute value inequalities are just another form of compound inequalities. An absolute value inequality can have a form such as the absolute value of x is less than m. This means that x is restricted to points on the number line less than m units from 0, in either the positive or the negative direction. Therefore, the absolute value of x is less than m is completely equivalent to negative m is less than x, which is less than positive m. Let's look at a clear example to understand this perfectly. Suppose we want to solve and graph the absolute value of x is less than 4. Based on the definition, this means x represents all numbers whose distance from 0 is strictly less than 4 units. So, we can rewrite this absolute value inequality into a sandwich compound inequality. Negative 4 is less than x, which is less than 4. Let's look at the graph. We place open circles at both endpoints, negative 4 and positive 4, because the distance is strictly less than 4. Then, we draw a bold red line connecting them in the middle. In interval notation, the solution set is written as the open interval from negative 4 to 4. Today we will learn how absolute value inequalities can be written as conjunctions. An inequality of the form absolute value of mx plus c is less than v can be rewritten as the compound inequality negative v is less than mx plus c, which is less than v. Let's solve example 1. Solve the inequality absolute value of x minus 3 is less than 5. First, we rewrite this absolute value inequality as a conjunction. This gives negative 5 is less than x minus 3, which is less than 5. Next, to isolate x by itself in the middle, we add 3 to all 3 parts. This simplifies beautifully to negative 2 is less than x, which is less than 8. So, our solution interval is open interval negative 2 to 8. On the number line, we place open circles at negative 2 and 8 and bold the segment between them. Next, let's talk about converting absolute values into normal disjunctions. An absolute value inequality of the form absolute value of mx plus c is greater than v is the same as the disjunction mx plus c is less than negative v, or mx plus c is greater than v. Let's look at example 3. Solve the compound inequality absolute value of 2x minus 1 is greater than 5. First, we write the inequality as a disjunction. This gives 2x minus 1 is less than negative 5, or 2x minus 1 is greater than 5. To get x by itself, we add 1 to all parts, getting 2x is less than negative 4, or 2x is greater than 6. Then, dividing by 2, we get x is less than -2 or x is greater than 3. Our solution set in interval notation is the union of open interval -infinity to -2 and open interval 3 to infinity. On the graph, we place open circles at -2 and 3 and draw arrows pointing outwards to both sides. Welcome back. Today we are starting Chapter 4, Linear Equations and Their Graphs. Let's look at the overview of this chapter. We have 5 main sections, from the coordinate plane to inequalities. In this specific lesson, we will focus on Section 4.1, the coordinate plane, and Section 4.2, lines. Let's get started. A plane is a flat surface that extends indefinitely in all directions. To locate points on a plane, we draw 2 perpendicular number lines. The horizontal number line is the x-axis, and the vertical number line is the y-axis. Their point of intersection is called the origin, and points are located using an ordered pair of coordinates. Let's look at example 1. Plot the coordinates 4, 2 on a graph. The first number 4 is the x-coordinate, representing the horizontal distance from the origin. So, we count 4 units across to the right on the x-axis. The second number 2 is the y-coordinate, representing the vertical distance. We count 2 units up parallel to the y-axis. Let's follow the dashed lines from the axes. Where they cross, we place our final solid point and label it as 4, 2. This beautifully defines our position on the plane. Sometimes we need to plot more than one point. You can often join up several plotted points to create the outline of a geometric shape. By connecting consecutive points, we can form polygons and calculate their dimensions, such as the lengths of their sides and their total perimeter. Let's solve example 2. Plot and label the points M, 4, 2, A, -4, 2, C, -4, -2, and V, 4, -2. Connect the points and find the perimeter of the resulting quadrilateral. First, let's locate each vertex on our coordinate plane. Counting the grid squares, the rectangle has a length of 8 units horizontally and a width of 4 units vertically. The perimeter formula is 2 times the length plus 2 times the width. This gives 16 plus 8, which simplifies to a final perimeter of 24 units. The coordinate axes divide the plane into 4 regions called quadrants. The quadrants are numbered counterclockwise using Roman numerals. The signs of the coordinates differ from quadrant to quadrant. Let's learn the sign rules for all 4 quadrants. Let's examine each quadrant on the grid. In quadrant 1, on the top right, both x and y are positive. Moving counterclockwise to quadrant 2 on the top left, x is negative and y is positive. Quadrant 3, on the bottom left, has both x and y as negative numbers. Finally, quadrant 4 on the bottom right has a positive x and a negative y. Simply by looking at the signs of the coordinates, you can easily tell where a point lies. Some points in the plane lie directly on the coordinate axis. All points whose coordinates are in the form x, 0 are located on the x-axis. All points whose coordinates are in the form 0, y are located on the y-axis. If neither coordinate is 0, the point lies in one of the quadrants, not on an axis. Let's solve example 2. State which axis, if either these points lie on. For A, the point is 0, 4. Since the x-coordinate is 0, it lies on the y-axis. For B, the point is 7, 3. Since neither x nor y is 0, it is not on an axis. For C, the point is 8, 0. Since the y-coordinate is 0, it lies on the x-axis. A straight line extends indefinitely in opposite directions. Lines have no endpoints, meaning they have no beginning or end. They have infinite length and no thickness. To draw a straight line, you simply need to plot 2 points on it and connect them. Let's look at example 1. Draw the straight line defined by the points -3, 1 and 3, -1. First, we plot the 2 points on the coordinate plane. Then, we connect them using a straightedge. Notice the arrowheads at both ends of the line. These show that the line continues indefinitely without ending. A straight line can be described mathematically by an algebraic equation. All the points that lie on the line have coordinates x, y that satisfy this relationship. For instance, an equation defines how to find the y-coordinate for any given value of x. This rule is called the equation of the line. Let's solve example 2. The points on the line y equals 3x plus 2 are defined by the form x, 3x plus 2. Find the coordinates of the points where x is a member of 0, 1, and 2. We substitute each value of x into the expression. When x equals 0, the coordinate is 0, 2. When x equals 1, we get 1, 5. And when x equals 2, it becomes 2, 8. So the resulting coordinates are 0, 2, 1, 5, and 2, 8. Points with the same x-coordinate are all the same horizontal distance from the y-axis. Therefore, a set of points that all share the same x-coordinate will fall on a vertical line. The equation of a vertical line is written as x equals c, where c is a fixed constant number. On this line, the x value never changes, regardless of what the y-coordinate is. Let's look at example 1. Draw and label the vertical lines x equals -2 and x equals 3. For the line x equals -2, we find -2 on the x-axis and draw a line straight up and down. For the line x equals 3, we find +3 on the x-axis and draw another vertical line. Notice that while the y-coordinates are completely different for each point on these lines, the x value stays exactly the same all the way through. The equation of a horizontal line is written in the form y equals c, where c is a constant fixed number. On a horizontal line, the values of the x-coordinates are completely different for each point, but the values of y stay exactly the same all the way through. Let's look at example 2. Draw and label the horizontal lines y equals 3 and y equals -2. For the line y equals 3, we find +3 on the y-axis and draw a straight line left and right. For the line y equals -2, we find -2 on the y-axis and draw another horizontal line. Notice that while the x-coordinates are different for each point on these lines, the y value remains completely unchanged. An equation in two variables x and y is linear if the variables have an exponent of 1. It can be written in the standard form, ax plus by equals c. The solution set consists of all ordered pairs x, y that satisfy the equation. All the points in this solution set lie on a straight line, which forms the graph of the equation. Let's explore the graph of the linear equation 3x plus 2y equals 6. To find points on this line, we can search for ordered pairs that make the equation true. For example, let's test the pair 0, 3. 3 times 0 plus 2 times 3 equals 6, so it is a solution. Next, let's test 2, 0. 3 times 2 plus 2 times 0 equals 6, so it is also a solution. When we plot these points and draw a line through them, we get a beautiful straight line. To determine if a point lies on the graph of an equation, we substitute the x and y coordinates into the equation. If the substitution results in a true statement, the point lies on the graph. If it results in a false statement, the point does not lie on the graph. Let's solve example 1. For a, we substitute 3 for x and -2 for y into the equation x minus 4y equals 11. This gives 3 minus 4 times -2, which simplifies to 3 plus 8 equals 11. Since 11 equals 11 is a true statement, the point 3, -2 lies on the line. For b, we substitute -2 for x and 3 for y into 3x plus 2y equals 5. This gives -6 plus 6 equals 0. Since 0 does not equal 5, it is a false statement, meaning the point -2, 3 does not lie on the graph. To graph a linear equation using 2 points, first rearrange the equation so it is in the slope-intercept form, y equals px plus q. Next, choose 2 values of x and substitute them to find the corresponding y values. Plot these 2 points and draw a straight line through them. Finally, choose a third point to check that your line is completely correct. Let's solve example 1. Plot and label the graph of the equation x minus y equals -2. First, we rearrange this equation to get y equals x plus 2. Let's choose 2 values of x. When x is -2, y is 0, giving the point -2, 0. When x is 3, y is 5, giving the point 3, 5. Let's plot these and draw a straight line. To check, let's use a third point where x equals 1. This gives y equals 3. Since the point 1, 3 lies perfectly on our line, our graph is completely correct. If a point lies on a line, then its coordinates must satisfy the equation of that line. This means if you substitute the coordinates for x and y into the equation, it will make a true mathematical statement. We can use this property to calculate unknown values, such as finding a missing variable k. Let's solve example 1. The point 3k, 2 is on the line x minus 2y equals 8. Find k and justify your answer. First, let's substitute 3k for x and 2 for y into the equation. This gives 3k minus 2 times 2 equals 8. Simplifying the multiplication, we get 3k minus 4 equals 8. By the addition property of equality, we add 4 to both sides, which gives 3k equals 12. Finally, dividing both sides by 3, we beautifully find that k equals 4. So, the actual point on the line is 12 too. We can also use the coordinates of a known point to identify an unknown value in the equation. Even if the question looks a bit different, the core mathematical method remains exactly the same. Simply substitute the given x and y values into the linear expression to solve for the missing coefficient b. Let's look at example 3. The point 2, 1 lies on the line bx plus 2y equals 8. Find the value of b. To solve this, we substitute 2 for x and 1 for y into the equation. This gives b times 2 plus 2 times 1 equals 8. Simplifying the expression, we get 2b plus 2 equals 8. Subtracting 2 from both sides gives 2b equals 6. Finally, dividing by 2, we find that b equals 3. Therefore, our complete line equation is 3x plus 2y equals 8. The x-intercept of a graph is the specific point where the line crosses the x-axis. Every single point on the horizontal x-axis has a y-coordinate of 0. Therefore, all points on this axis are always written in the form x, 0. To find the x-intercept from any linear equation, we can simply substitute y equals 0 and solve for x. Let's solve example 1. Find the x-intercept of the line 4x minus 3y equals 12. Since we know the x-intercept always has a y-coordinate of 0, we let y equal 0. Substituting 0 into the equation gives 4x minus 3 times 0 equals 12. This simplifies directly to 4x minus 0 equals 12, which means 4x equals 12. Dividing both sides by 4, we find that x equals 3. Therefore, the coordinates 3, 0 define the exact x-intercept of this line. Since the y-intercept has an x-coordinate of 0, we can always find the y value by letting x equal 0 in the equation of the line. Every single point on the vertical y-axis has an x-coordinate of 0. Therefore, all points on this vertical axis are written in the form 0, y. Substituting x equals 0 simplifies the linear equation, leaving only the y variable to solve. Let's solve example 3. Find the y-intercept of the line negative 3x minus 4y equals negative 12. First, we let x equal 0, then solve for y. Substituting 0 for x gives negative 3 times 0 minus 4y equals negative 12. This simplifies directly to 0 minus 4y equals negative 12, which means negative 4y equals negative 12. Dividing both sides by negative 4, we find that y equals positive 3. Therefore, the coordinates 0, 3 define the exact y-intercept of this line. To graph a straight line by computing the intercepts, first find the x-intercept by letting y equal 0, then solve for x. Next, find the y-intercept by letting x equal 0, then solve for y. Draw a set of axes, plot both intercept points, and draw a straight line through them. Finally, verify your work by checking a third point on the line. Let's solve example 1. Draw the graph of 3x plus 4y equals 12 by computing the intercepts. To find the x-intercept, let y equal 0. This gives 3x equals 12, so x equals 4. Our x-intercept point is 4, 0. To find the y-intercept, let x equal 0. This gives 4y equals 12, so y equals 3. Our y-intercept point is 0, 3. Let's check using a third point. If x equals negative 4, substituting it gives y equals 6. Since the checkpoint negative 4, 6 lies perfectly on our path, the line is absolutely correct. Welcome back. In this section, we continue our journey through Chapter 4. We have already covered the coordinate plane and basic lines. Now, in this specific lesson, we will thoroughly explain Section 4.3, Slope, Section 4.4, More lines, and Section 4.5, Inequalities. Let's master these concepts. The slope or gradient of a line is a measure of its steepness. The slope of a straight line is the ratio of the vertical change to the horizontal change between any 2 points lying on the line. The vertical change is often called the rise, and the horizontal change is often called the run. Therefore, slope is given by the formula rise over run, or delta y over delta x. Let's look at an example. A line passes through 2 points, P1 at 1, 2, and P2 at 5, 5. Let's find the slope using the coordinate formula. We substitute the coordinates into the formula, y2 minus y1 over x2 minus x1. This gives 5 minus 2 in the numerator and 5 minus 1 in the denominator. Simplifying the fractions, we get a rise of 3 and a run of 4. So, our final slope m is exactly 3 over 4, which equals 0.75. Since the slope is positive, the line goes uphill from left to right. To find the slope of a line passing through 2 points, we use the standard slope formula m equals y2 minus y1 over x2 minus x1. Simply substitute the given coordinates into this algebraic expression. Once we find the slope, we can easily draw the graph by plotting the 2 points and joining them up with a straight line. Let's solve example 1. Find the slope of the line that passes through the points 1, 1, and 4, 5, and draw the graph. Let's substitute the values into our slope formula. In the numerator, y2 minus y1 gives 5 minus 1. In the denominator, x2 minus x1 gives 4 minus 1. Simplifying this expression, we get 4 over 3. So the final slope of the line is exactly 4 over 3. When a coordinate contains an unknown variable like k, we can still find its value by applying the standard slope formula. Let's substitute the coordinates into the formula, set it equal to the given slope, and solve the equation step by step. Let's solve a similar practice problem. If the slope of the line that passes through the points 2, 3, and 5, 3k is 2, find the value of k. First, substituting the values into our slope formula gives 3k minus 3 over 5 minus 2. This simplifies to 3k minus 3 over 3. Since the given slope is 2, we can write the equation as 3k minus 3 over 3 equals 2. Multiplying both sides by 3, we get 3k minus 3 equals 6. Adding 3 to both sides gives 3k equals 9. Finally, dividing by 3, we find that k equals 3. If we know the slope m and a specific point x1, y1 on a line, we can determine the complete equation of that straight line. Let's geometrically derive why the point slope formula works from the fundamental definition of slope. By definition, the slope m between any 2 points on a line is the change in y divided by the change in x. For our fixed point x1, y1, and the generic point x, y, the slope can be expressed as y minus y1 divided by x minus x1 equals m. To eliminate the fraction, let's multiply both sides of the equation by x minus x1. As a result, we successfully derive the point-slope formula, y minus y1 equals m times x minus x1. Let's practice finding the equation of a straight line using the point-slope formula. When we are given a specific coordinate and the slope of the line, we can substitute these values directly into the formula, y minus y1 equals m times x minus x1, and simplify it into its standard algebraic form. Let's solve our practice problem. Find the equation of the line through the point 3, -2 that has a slope of -2. Here, our fixed point x1, y1 is 3, -2, and the slope m is -2. Substituting these into the formula, we get y minus -2 equals -2 times x minus 3. This simplifies to y plus 2 equals -2x plus 6. Finally, rearranging the variables to the left side, we get 2x plus y equals 4. This is our final equation of the straight line. Parallel lines are two or more lines in a plane that never intersect or cross. No matter how long you draw them, they will never meet. We use a special symbol with two vertical bars to indicate that lines are parallel. Let's look at how this appears on a coordinate plane. Let's define the mathematical notation. If line L1 and line L2 are parallel, we read this as line L1 is parallel to line L2. Algebraically, parallel lines are very special because they always share the exact same slope. This means if line L1 has a slope of m1 and line L2 has a slope of m2, then m1 must equal m2. Vertical lines are parallel to each other, but they have a very unique property. Their slopes are completely undefined. Let's explore algebraically and geometrically why the slope of a vertical line cannot be defined. Any 2 points on a vertical line will always have the same x-coordinate, which we can call C. So the points look like C, y1 and C, y2. When we substitute these into the standard slope formula, the denominator becomes C minus C, which equals 0. Because dividing any number by 0 is undefined, the slope m is not defined. Two lines are perpendicular if they intersect at a perfect 90-degree right angle. Algebraically, their slopes have a very unique relationship. The slope of one line is the negative reciprocal of the slope of the other. Let's break down what this means mathematically. To get the reciprocal of a number, you divide 1 by that number. For example, the reciprocal of x is 1 over x, so its negative reciprocal is -1 over x. Therefore, if two lines L1 and L2 are perpendicular, the product of their slopes, m1 times m2, must equal -1. Let's see this visually. To find the equation of a line perpendicular to another line, we first need to determine the slope of the original line. Then, we find its negative reciprocal to get our perpendicular slope. Finally, we apply the point-slope formula with our new coordinates. Let's solve the practice problem. Determine the equation of the line passing through 4, 3 that is perpendicular to the line through 1, -2 and 3, 2. Step 1. Find the original slope m1. The difference in y over difference in x gives 2 minus negative 2 over 3 minus 1, which equals 4 over 2, or exactly 2. Step 2. Find our perpendicular slope m2. Since m1 times m2 equals negative 1, 2 times m2 equals negative 1, giving us a slope of negative 1 over 2. Step 3. Use the point-slope formula. Substituting the point 4, 3, and our new slope, y minus 3 equals negative 1 over 2 times x minus 4. Multiplying both sides by 2 and rearranging the terms, we get our final equation x plus 2y equals 10. The slope-intercept form is one of the most common ways to express a linear equation. In this form, the variable y is isolated on one side of the equation. Let's mathematically prove why y equals mx plus b represents a straight line. To prove this, let's start with a line that has a slope of m and crosses the y-axis at b. This crossing point means the line passes through the fixed point 0, b. Now let's apply the standard point-slope formula, which is y minus y1 equals m times x minus x1. Substituting our point 0, b into this expression gives y minus b equals m times x minus 0. Simplifying the right side gives y minus b equals mx. Finally, adding b to both sides isolates y, leaving us with y equals mx plus b. The formula is beautifully proven. To plot the graph of a linear equation in slope-intercept form, we begin by identifying the y-intercept and plotting that point first. From there, we use the rise over run definition of the slope to find a second point and connect them with a straight line. Let's solve our practice problem. Plot the graph of y equals 1 over 3x plus 1. First, comparing this with y equals mx plus b, the y-intercept b is 1, so we plot the point 0, 1. Next, the slope m is 1 over 3. This means for a slope of 1 over 3, we go up 1 unit for every 3 units across. Starting from 0, 1, moving 3 units right and 1 unit up brings us to the point 3, 2. Now let's see how to plot this on the coordinate plane. When a linear equation is given in general form, we can find its slope and y-intercept by converting it into slope-intercept form. To do this, we isolate the variable y on one side step by step and then simply read the coefficients. Let's solve the practice problem. Determine the slope and y-intercept of the line 3x minus 4y equals 8. Step 1. Solve the equation for y. Subtract 3x from both sides to get negative 4y equals negative 3x plus 8. Next, divide everything by negative 4. This gives y equals negative 3 over negative 4x plus 8 over negative 4. Simplifying the signs, we get y equals 3 over 4x minus 2. Step 2. Extract the values. The slope m is exactly 3 over 4, and the constant term is negative 2, meaning the y-intercept is 0, negative 2. Let's graph this line to see the final result. Since parallel lines share the exact same slope, we can find our new line's equation by extracting the slope from the given line. Then, we substitute the slope along with the new coordinates into the point-slope formula. Let's solve the practice problem. Find the equation of the line through 2, one that is parallel to the line 3x minus y equals 4. Step 1. Rearrange the given line into slope-intercept form to find y equals 3x minus 4. This shows the original slope is 3. Step 2. Since the required line is parallel, its slope must also be exactly 3. Step 3. Apply the point-slope formula. Substituting our point 2, 1 and slope 3, y minus 1 equals 3 times x minus 2. Expanding and rearranging the terms, we get our final parallel line equation, 3x minus y equals 5. Two lines with the exact same slope can either be parallel or coinciding. If their y-intercepts are different, the lines will never meet and are parallel. However, if their y-intercepts are also identical, the two lines lie exactly on top of each other. Let's compare two examples with a slope of 2. First, look at y equals 2x plus 1 and y equals 2x minus 3. They have the same slope but different y-intercepts, making them parallel. Second, consider y equals 2x plus 1 and 2x minus y equals negative 1. Converting the second equation gives y equals 2x plus 1. Since the slope and y-intercept are both identical, these lines coincide completely. A single line divides the entire two-dimensional coordinate plane into 3 distinct regions. First, the set of points that lie exactly on the line. Second, the region of points that lie strictly above the line. And third, the region of points that lie strictly below the line. Let's practice with the linear equation y equals x plus 1. The points on this line form a boundary and satisfy y equals x plus 1. Since the boundary line itself is not included in the strict inequalities, the line will be drawn as a dashed line. The area above satisfies y is greater than x plus 1, and the area below satisfies y is less than x plus 1. To sketch the region defined by a linear inequality, we first plot the corresponding equation as our borderline. Then, to decide which side to shade, we test a simple point like 0, 0. If the statement is true, we shade that side. If false, we shade the opposite side. Let's solve our practice problem. Sketch the region defined by 2x minus y is greater than 1. First, the borderline equation is 2x minus y equals 1, which simplifies to y equals 2x minus 1. Next, let's test the point 0, 0. Substituting x equals 0 and y equals 0 gives 0 minus 0 is greater than 1. Since 0 is not greater than 1, this is a false statement. Therefore, 0, 0 does not lie in our region, so we shade the opposite side of the line. Inequality regions can have different types of borders. A strict inequality using greater than or less than signs does not include the border, so we draw it as a dashed line. However, inequalities with greater than or equal to or less than or equal to do include the border, so we draw it as a solid line. Let's visualize this using a custom example. Y is greater than negative x plus 2. Because this is a strict inequality, we sketch the region above the line and make the border dashed. Now, if we change the sign to greater than or equal to, the boundary line's points are now included, and the dashed line transforms into a solid line. Let's solve a similar practice problem step by step. To sketch the region for the inequality 3y is less than 3x plus 6, we first convert it to a standard boundary equation. Then we check a test point to find the correct side to shade. First, let's form the borderline equation. 3y equals 3x plus 6. Dividing both sides by 3 gives y equals x plus 2. Since the sign is strictly less than, the line will be dashed. Now, test whether the point 0, 0 satisfies the inequality. Substituting x equals 0 and y equals 0 gives 0 is less than 6. This is a true statement, so 0 lies inside our solution set. A system of linear inequalities consists of two or more inequalities. The solution to the system is the region that satisfies all inequalities at the same time. To graph this system, we find the overlapping area where the individual regions intersect. Let's solve a system with two custom inequalities. Y is greater than x minus 1 and y is less than negative x plus 3. We will graph the first region, then graph the second region, and finally locate the exact boundary where they completely overlap. Welcome. Today, we are going to master Chapter 5, Systems of Equations. In this comprehensive session, we will cover all three core sections together. First, Section 5.1 introduces the foundational concept of systems of equations. Next, Section 5.2 explores the powerful algebraic tool known as the elimination method. Finally, Section 5.3 guides us through the practical applications of systems of equations. Let's master this entire chapter in this class. A system of linear equations consists of two or more linear equations in the same variables. Let's look at this system. The solution to this system is an ordered pair x and y that satisfies both equations simultaneously at the same time. By testing the values x equals 3 and y equals 2, we can verify it makes both equations true. Graphically, this unique solution represents the single point of intersection where the two lines cross. Let's practice solving a similar system of equations by graphing. Our system is x minus 2y equals negative 4 and 2x plus y equals 7. In step 1, we rewrite both equations in slope-intercept form to graph them. The first line transforms into y equals 1/2 x plus 2, passing through points 0, 2 and 2, 3. The second line becomes y equals negative 2x plus 7, passing through 2, 3, and 3, 1. In step 2, we plot them together and read the point of intersection, which is exactly 2, 3. Finally, in step 3, we substitute these coordinates back into both original equations to verify. Since both equations yield perfectly true statements, 2, 3 is our definitive solution. The substitution method involves more algebra than graphing, but it gives us highly accurate solutions. First, we take one equation and solve it for one variable, such as y. Next, we substitute this expression into the other equation, creating an equation with just one single variable. We solve for x and then substitute that value back to find our second variable. Let's trace this entire algebraic process step by step without any shortcuts. Let's solve a similar example using the graphing method. Our system consists of 3y plus x equals 9 and 3y plus 2x equals 12. In step 1, we isolate y to rewrite both equations in slope-intercept form. The first line becomes y equals negative 1/3 x plus 3, passing through points 0, 3, and 3, 2. The second line transforms into y equals negative 2/3 x plus 4, passing through 0, 4, and 3, 2. In step 2, plotting these lines reveals their unique point of intersection at exactly 3, 2. Finally, in step 3, we substitute x equals 3 and y equals 2 back into our original equations. Since both equations result in perfectly true statements, the pair 3, 2 is our final solution. So far, we have looked at systems with exactly one solution. However, some systems of linear equations have no solutions at all. A system of equations with no solutions is called an inconsistent system. Let's trace this system by graphing. When we convert both equations into slope-intercept form, we see that both lines have the exact same slope of negative 2, but different y-intercepts. Because their slopes are equal, the two lines are perfectly parallel and will never intersect. Since there is no point of intersection, the system has no solutions. Let's solve a dependent system of equations by graphing. Our new system is y plus 2x equals 3 and 3y plus 6x equals 9. First, let's rearrange both equations into slope-intercept form to find their points. Step 2. Let's graph both equations on the same coordinate plane. As you can see, both equations represent the exact same line. Therefore, the lines coincide completely, giving us infinitely many points of intersection. The system is dependent, having infinitely many solutions. When graphing is difficult or inaccurate, we use the elimination method. Let's solve our new system. Minus 2y plus 3x equals 8 and 4y minus x equals 4. Our first step is to make the coefficients of one variable have the same absolute value. Let's multiply the entire second equation by 3. 3 times the quantity 4y minus x equals 3 times 4. This gives us a new equivalent equation, 12y minus 3x equals 12. Step 2. Now add the two equations together to eliminate the variable x. Minus 2y plus 12y is 10y. The 3x and minus 3x cancel out to 0. And 8 plus 12 equals 20. Dividing by 10, we beautifully find y equals 2. Let's solve a system of linear equations with fractional coefficients. Our problem is 1 over 2a plus 2 over 3b equals 7 over 6, and 3 over 4a minus 1 over 2b equals 1 over 4. To make it simpler, we will clear the fractions by multiplying each equation by its least common multiple. Let's clear the fractions. Multiplying the first equation by 6 gives 3a plus 4b equals 7. Multiplying the second equation by 4 gives 3a minus 2b equals 1. Now we have a beautiful system of integer equations. Step 2. Notice that the coefficient of a is 3 in both equations. We can eliminate a by subtracting the second equation from the first. 3a minus 3a is 0. For b minus 2, b becomes 6b. And 7 minus 1 equals 6. Dividing both sides by 6, we get b equals 1. Step 3. Finally, substitute b equals 1 back into one of our integer equations. Let's use 3a minus 2b equals 1. Substituting b gives 3a minus 2 equals 1. Adding 2 to both sides, 3a equals 3, which means it equals 1. Our final solution is it equals 1 and b equals 1. Let's solve an age word problem using systems of equations. The sum of Jose's and Elizabeth's current ages is 44 years. For years ago, Elizabeth was 5 times as old as Jose. Let's define x as Jose's current age and y as Elizabeth's current age. Step 1. Let's form our system of equations. Since the sum of their present ages is 44, our first equation is x plus y equals 44. For years ago, their ages were x minus 4 and y minus 4. Elizabeth was 5 times Jose's age, so y minus 4 equals 5 times the quantity x minus 4. Simplifying this gives our second equation, y minus 5x equals minus 16. Step 2. Let's align and solve the system of equations. Since the y coefficients are the same, we can eliminate y by subtracting the second equation from the first. Y minus y cancels out. X minus 5x becomes 6x. And 44 minus 16 beautifully equals 60. Dividing by 6, we find that x equals 10. Jose is 10 years old. Step 3. Now substitute x equals 10 back into our first original equation. 10 plus y equals 44. Subtracting 10 from both sides, we beautifully find y equals 34. Therefore, today, Jose is 10 years old and Elizabeth is 34 years old. We have successfully solved the Chapter 5 age problem. Let's solve a number word problem using the substitution method. The sum of two integers is 48. The larger number is 3 less than 4 times the smaller one. Let's define x as the smaller number and y as the larger number. Step 1. Let's write the system of equations. Since their sum is 48, our first equation is x plus y equals 48. The second condition tells us that y equals 4x minus 3. Because the second equation directly expresses y in terms of x, it makes perfect sense to use substitution. Step 2. Let's substitute 4x minus 3 for y in the first equation. This gives us x plus the quantity 4x minus 3 equals 48. Combining like terms, we get 5x minus 3 equals 48. Adding 3 to both sides gives 5x equals 50. Dividing both sides by 5, we perfectly find x equals 10. Step 3. Now substitute x equals 10 back into our second equation to find y. Y equals 4 times 10 minus 3. 4 times 10 is 40, and minus 3 gives 37. Therefore, the smaller number is 10, and the larger number is 37. We have successfully checked and solved this substitution problem. Let's solve a river current word problem. A rescue boat travels 90 miles downriver in 3 hours. Returning upriver, it takes 5 hours to travel the same 90 miles. Let's find the speed of the boat in still water and the speed of the current. Step 1. Let's form our equations using the formula rate times time equals distance. When going downriver, the effective speed increases to be plus c. Multiplying by 3 hours gives 90 miles, which simplifies to be plus c equals 30. Upriver, the current fights the boat, making the speed be minus c. Multiplying by 5 hours gives 90 miles, simplifying to be minus c equals 18. Step 2. Let's solve the system by adding the two equations together. Since the current terms have opposite signs, they will cancel out. b plus b equals 2b. Positive c and negative c become 0. And 30 plus 18 equals 48. Dividing both sides by 2, we beautifully find that b equals 24 miles per hour. Step 3. Finally, let's substitute b equals 24 back into the first equation. 24 plus c equals 30. Subtracting 24 from both sides, we perfectly find c equals 6. So, the boat's speed in still water is 24 miles per hour, and the speed of the water current is 6 miles per hour. The motion problem is fully solved. Welcome back. Today, we entered Chapter 6, Manipulating Polynomials. In this comprehensive curriculum, we will explore the structural foundations of polynomials. Let's look at our roadmap, from adding and subtracting to multiplying and dividing expressions. In this specific session, we are going to fully master 3 core parts together. We will completely cover Section 6.1, Section 6.2, and Section 6.3 in today's class. Get ready to dominate addition, subtraction, multiplication, and division of polynomials. First, let's learn about monomials. A monomial is a single-term expression. It can be either a standalone number or a product of a number and one or more variables. For example, 13, 2x squared, and minus x cubed yn to the fourth are all monomials. Next, a polynomial is an algebraic expression with one or more terms. There are a couple of special types of polynomials. A binomial has exactly 2 terms, such as x squared plus 1. A trinomial has exactly 3 terms, such as minus 3x squared plus 2x plus 1. Let's learn how to simplify polynomials using like terms. Like terms are terms that have exactly the same variables with the same exponents. They always have the same variables, but they can have different coefficients. A polynomial can often be simplified beautifully by combining all of these like terms. Let's solve example 1. Simplify the new algebraic expression, 4x squared plus 7y plus 5x squared. Notice that there are 2 like terms in this expression, 4x squared and 5x squared. We can combine these 2 like terms beautifully. 4x squared plus 5x squared equals 9x squared. Therefore, our simplified expression is 9x squared plus 7y. Let's explore the opposite of a polynomial. The opposite of a number is its additive inverse. For instance, the opposite of a positive number is its corresponding negative number. To find the opposite of a polynomial, you simply make the positive terms negative and the negative terms positive. We change the signs of every single term. Let's solve example 1 with our new polynomials. For part A, find the opposite of 4x minus 3. By flipping the signs, positive 4x becomes minus 4x, and minus 3 becomes plus 3. The answer is minus 4x plus 3. For part B, find the opposite of minus 2x squared plus 5x minus 7. Reversing every sign gives us positive 2x squared, minus 5x, and plus 7. Let's learn how to add polynomials using two different methods. Our new problem asks us to find the sum of three polynomials. Method A consists of collecting like terms and simplifying. First, we open all the parentheses. Then, we group the x squared terms, the x terms, and the constant numbers together to get x squared plus 7x minus 4. Now let's check method B, vertical lining up of terms. We line up the like terms vertically in columns. In the first column, minus 4x squared plus 5x squared is x squared. In the second column, 5x minus x plus 3x is 7x. Finally, minus 2 plus 4 minus 6 gives minus 4. Both methods give us the exact same beautiful solution. Let's learn how to multiply a polynomial by a number. Multiplying a polynomial by a number is fundamentally the same as adding the entire polynomial together several times. For example 3, let's multiply x plus 4 by 4. This means we add x plus 4 to itself 4 times, which groups into x plus x plus x plus x and 4 plus 4 plus 4 plus 4. However, adding repeatedly is too slow. The simpler, faster way to do this is to multiply each term of the polynomial directly by the number outside. In other words, you expand the parentheses using the distributive property. 4 times x is 4x, and 4 times 4 is 16, instantly giving us 4x plus 16. Let's learn how to subtract polynomials. Subtracting polynomials is conceptually the same as subtracting regular numbers. To subtract polynomial a from polynomial b, we need to subtract each individual term of a from b. Our new example sets polynomial a as x squared plus 2x and polynomial b as x squared plus 6x. Let's set up the expression polynomial b minus polynomial a. Now, let's expand the parentheses to simplify the expression. Remember to distribute the negative sign into each term of polynomial a. This transforms positive x squared into minus x squared and positive 2x into minus 2x. Grouping like terms, x squared minus x squared cancels out to 0. Finally, 6x minus 2x beautifully gives us our final answer for x. Let's look at another way to understand subtracting polynomials. Subtracting a polynomial is simply the same as adding its opposite. In example 2, let's subtract minus 4x squared plus 5x minus 7 from minus 6x squared plus 2x plus 4. We distribute the negative sign, which flips the signs of the second polynomial into plus 4x squared, minus 5x, and plus 7. Combining like terms, we get minus 2x squared minus 3x plus 11. Alternatively, example 3 shows how to do this subtraction by lining up terms vertically. We can change the subtraction operation to addition by writing the opposite of each term in the second row. Minus 4x squared becomes plus 4x squared, plus 5x becomes minus 5x, and minus 7 becomes plus 7. Adding downward column by column, we beautifully get the exact same solution, minus 2x squared minus 3x plus 11. Let's solve a geometric problem using polynomials. We have two rectangles, P1 and P2, with algebraic expressions for their sides. Our ultimate goal is to find both the sum and the difference of their perimeters. Remember, the perimeter means the total distance around the outside of a shape. Step 1. Let's calculate the perimeter expressions for each rectangle. Since a rectangle has two lengths and two widths, we multiply the sum of adjacent sides by 2. For P1, 2 times the quantity of its sides beautifully simplifies to 6x squared minus 2x minus 6. For P2, doing the exact same multiplication results in 4x squared plus 2x. Finally, let's find the sum and difference between the two perimeters. For question A, adding the expressions gives 10x squared minus 6. For question B, subtracting P2 from P1 and distributing the negative sign beautifully gives us 2x squared minus 4x minus 6. We have successfully solved this geometric polynomial problem. Welcome back. Let's review the 7 essential rules of exponents. First, multiplying same bases adds exponents, and dividing subtracts them. Powers of powers multiply exponents, and a product raised to a power distributes it. Fractional exponents convert to radicals, negative exponents create fractions, and any base raised to the power of 0 beautifully equals 1. Now, let's practice example 1. Simplify the expression, open parenthesis, minus 3a cubed b squared, close parenthesis, times open parenthesis, minus 4a squared b to the 4th, close parenthesis. First, group all like parts together. Multiply the coefficients, minus 3 times minus 4. Then, use Rule 1 to add the exponents of same variables. This beautifully results in 12, a to the 5th, b to the 6th. Finally, let's look at example 2. Simplify the expression, the quantity of 2p to the 4th q squared, all raised to the power of 3. Here, we must distribute the outer exponent 3 to every factor inside using Rule 4. Then, apply Rule 3 to multiply the exponents. 2 cubed is 8, p becomes 4 times 3 which is 12, and q becomes 2 times 3 which is 6. Our final answer is 8p to the 12th, q to the 6th. Let's explore how to multiply a polynomial by a monomial. Just like multiplying a polynomial by a regular number, we will use the distributive property. This means we multiply each term inside the polynomial separately by the monomial outside. Let's look at our new example 1. Simplify the algebraic expression, minus 3x times the quantity of 2x plus 4x squared. Now, let's expand the expression step by step. We multiply the binomial terms by the monomial minus 3x. First, minus 3x times 2x gives minus 6x squared. Next, minus 3x times positive 4x squared results in minus 12x cubed. Combining these parts, our beautifully simplified final answer is minus 6x squared minus 12x cubed. Let's learn how to multiply a binomial by a trinomial. This process is an extended version of the distributive property. We will distribute every single term of the first binomial into the entire second trinomial. Let's look at our new example 5. Simplify the algebraic expression, the quantity of x plus 3 times the quantity of x squared plus 3x plus 2. Now let's expand the expressions carefully. First, distribute x to the trinomial, which gives x cubed plus 3x squared plus 2x. Next, distribute positive 3, which gives 3x squared plus 9x plus 6. Now, combine the like terms together. 3x squared plus 3x squared is 6x squared, and 2x plus 9x is 11x. Our fully simplified final answer is x cubed plus 6x squared plus 11x plus 6. Did you know you can multiply polynomials just like regular numbers? We call this the stacking method. For example, let's multiply 63 by 27 by stacking them vertically. Notice how the multiplication sign stays on the far left, keeping our numbers perfectly aligned. 7 times 63 is 441, and 20 times 63 is 1,260, giving us 1701. Now let's apply the exact same vertical alignment to polynomials. We want to expand the product of 4x plus 3y and 2x plus 5y. Look how the multiplication sign stays perfectly on the left. First, multiply 4x plus 3y by 5y, which gives 20xy plus 15y squared. Next, multiply by 2x. We must align the 8x squared and 6xy precisely in the correct columns. Adding straight down column by column, our final answer is 8x squared plus 26xy plus 15y squared. Let's solve a geometric area problem by multiplying polynomials. We need to find the area of the space between two rectangles. The outer large rectangle has a length of 6x plus 8 and a width of 4x plus 3. The inner small rectangle is surrounded by a uniform border of width x on all sides. Let's look at this setup visually. Step 1. Let's find the exact dimensions of the middle inner rectangle. Since the border width x exists on both left and right sides, we subtract 2x from the outer length. 6x plus 8 minus 2x simplifies beautifully to 4x plus 8 inches. Similarly, we subtract 2x from the outer width. For x plus 3 minus 2x gives us 2x plus 3 inches. Step 2. Now let's find the area of the border space. The area of the space equals the large rectangle area minus the small rectangle area. We set up the expression, the product of 6x plus 8 and 4x plus 3 minus the product of 4x plus 8 and 2x plus 3. Expanding both polynomial products and carefully distributing the negative sign, the higher and constant terms beautifully simplify. Our final simplified answer is 16x squared plus 22x square inches. Let's solve a geometric volume problem by multiplying polynomials. We need to find the expression for the volume of the box on the right. The length is 4x plus 5, the width is 5x minus 4, and the height is 3x plus 4. Remember, the volume of a rectangular prism is found by multiplying its length, width, and height together. Step 1. Let's multiply the first two polynomials together, length times width. We expand the product of 4x plus 5 and 5x minus 3 using the distributive property. For x times 5x is 20x squared. For x times minus 3 is minus 12x. 5 times 5x is 25x, and 5 times minus 3 is minus 15. Combining the middle-like terms, we dynamically simplify it to 20x squared plus 13x minus 15. Step 2. Finally, we multiply this intermediate result by the height, 3x plus 4. We distribute each term of 3x plus 4 across the trinomial. 3x times the trinomial gives 60x cubed plus 39x squared minus 45x. 4 times the trinomial gives 80x squared plus 52x minus 60. By grouping and combining all the like terms according to the commutative law, our final simplified answer is 60x cubed plus 119x squared plus 7x minus 60 cubic inches. Let's learn how to simplify polynomials raised to a negative power. Just like regular variables, an entire polynomial expression raised to a negative power can also be written as a fraction by moving the whole base into the denominator. Let's master example 3 step by step by rewriting these expressions. Let's simplify example 3a. The expression is the quantity x plus y times the quantity x minus z raised to the minus 1 power. The negative exponent belongs only to x minus z. So, x minus z to the minus 1 becomes 1 over x minus z. Multiplying it together, our fraction is x plus y over x minus z. Next, let's solve example 3b. Simplify the quantity a minus b times a plus b times a minus b to the minus 1 power. Moving the negative power part to the bottom creates a single unified fraction, a minus b times a plus b, all over a minus b. Notice that the identical factor a minus b exists in both numerator and denominator. Canceling them out perfectly leaves our final simplified answer, a plus b. Finally, let's solve example 3c. Simplify the quantity p minus 2 to the power of minus 1 times p plus 2 to the power of minus 1. Both parentheses have negative powers, so both flip down into the denominator together. This gives us 1 over the product of p minus 2 and p plus 2. Expanding the denominator using the difference of squares formula, our final answer is 1 over p squared minus 4. Let's learn how to divide a polynomial by a monomial. To do this, we must use the rules of exponents. The particular rule that is useful here is the quotient rule x to the a divided by x to the b equals x to the a minus b power. Let's apply this core rule to simplify some expressions. Let's practice example 1. Divide 3x cubed by x. We can express this division as a fraction, 3x cubed over x. By applying the exponent rule, we subtract the invisible exponent, one of the denominator, from the numerator's exponent 3. This beautifully simplifies to 3x squared. Finally, let's solve example 2. Divide 3x to the 4th y plus x squared y cubed, all by xy. Using the distributive property, we split the expression and divide each term separately by xy. In the first part, 3x to the 4th y over xy simplifies to 3x cubed. In the second part, x squared y cubed over xy becomes xy squared. Combining them, our final simplified answer is 3x cubed plus xy squared. Let's explore how to find the reciprocal of a polynomial. The reciprocal of a polynomial is its multiplicative inverse. To find the reciprocal of any polynomial a, you simply divide the number 1 by polynomial a. By the definition of division, to divide by a polynomial, you need to multiply by the reciprocal of that polynomial. Let's solve example 1 with our new polynomials. Find the reciprocal of each of these expressions. For part A, the given polynomial is 3x minus 2. Its reciprocal is simply 1 over 3x minus 2. For part B, the given polynomial is minus 4x squared plus 5x minus 3. Placing 1 over the entire expression, its reciprocal is 1 over minus 4x squared plus 5x minus 3. Let's learn how to express fractions using negative exponents. The negative exponent rule tells us that x to the power of minus a is exactly equal to 1 over x to the a, provided that x is not 0. This essential rule gives us another powerful way to express and simplify fractions. Let's practice example 2a. Simplify 3 to the power of minus 3. Applying the negative exponent rule, this turns into 1 over 3 cubed. Expanding the denominator, 3 cubed is 3 times 3 times 3, which is 27. Our final simplified answer is 1 over 27. Next, let's look at example 2b. Simplify 4x times the quantity of 2y raised to the minus 1 power. The negative power belongs only to the parentheses of 2y. So, 2y to the minus 1 becomes 1 over 2y. Multiplying it by 4x creates the fraction for x over 2y. Finally, dividing 4 by 2 simplifies the entire fraction to 2x over y. Finally, let's solve example 2c. Simplify 8a to the 4th times the quantity of 2ab raised to the minus 2. First, rewrite the negative power part as 1 over the quantity of 2ab squared. Next, expand the denominator using the power rule. 2 squared is 4, creating 4a squared b squared. Combining them gives 8a to the 4th over 4a squared b squared. By dividing the coefficients and subtracting powers of a, our final answer is 2a squared over b squared. Let's explore how canceling fractions helps to simplify algebraic expressions. If a standard numerical fraction has a common factor in both the numerator and the denominator, we can cancel it out. For example, 4 over 12 can be written as 4 times 1 over 4 times 3. Canceling the common factor 4 beautifully leaves us with 1 over 3. Let's practice example 1 with our new algebraic fraction. We are asked to simplify the expression, the product of x plus 3 and 3x plus 2, all divided by the quantity x plus 3. This technique is incredibly useful for dividing polynomials when the expressions have already been factored for us. Now let's solve the problem. Notice that the identical factor, x plus 3, appears in both the numerator and the denominator. We can cancel out the group x plus 3 from both top and bottom completely. This removes them from our expression, leaving only the remaining factor. Therefore, our beautifully simplified final solution is 3x plus 2. Let's learn the long division method for dividing polynomials when there is a remainder. Our new problem asks us to divide 6x squared minus x minus 7 by 2x minus 3. First, consider the leading terms. 6x squared divided by 2x is 3x. We place 3x exactly above the 6x squared term on the quotient line. Then, We subtract the product of 3x and 2x minus 3, which is 6x squared minus 9x, leaving us with 8x minus 7. Next, see how many times the leading term 2x goes into the remaining leading term 8x. 8x divided by 2x is positive 4. We place plus 4 right next to 3x on the top line. Now, we subtract 4 groups of 2x minus 3, which is 8x minus 12, from our remaining terms. Minus 7 minus 12 is positive 5. Since 5 has a lower degree than 2x, our division stops here, leaving a final remainder of 5. Therefore, we can write our final solution as a statement. The fraction 6x squared minus x minus 7 over 2x minus 3 is beautifully equal to the quotient 3x plus 4, with a remainder of 5. The non-exact polynomial division is successfully solved. You can factor higher degree polynomials too. If you have a polynomial higher than degree 2, like a cubic equation, long division can help factor it. If you divide polynomial a by polynomial b and get a remainder of 0, then b is a perfect factor of a. Let's solve our new example. Divide 6x cubed plus 11x squared minus 19x minus 6 by 2x minus 3. First, 6x cubed divided by 2x gives 3x squared. Subtracting the product leaves us with 20x squared. Next, 20x squared divided by 2x is 10x. We place plus 10x on top. Subtracting the product leaves 11x minus 6. No, 30x minus 19x is 11x. Then, dividing the remaining terms gives a final constant of 2. Subtracting 2 groups of 2x minus 3 leaves exactly 0. The remainder is 0. Because the remainder is exactly 0, 2x minus 3 is a perfect factor. This also means that our original cubic polynomial can be factored beautifully into the product of 2x minus 3 and the quotient 3x squared plus 10x plus 2. If the quotient can be factored further, you can fully factor the entire polynomial. The higher degree factoring is complete. Volume problems often involve polynomials. In example 1, we are given a box with a volume represented by a cubic polynomial. We know the length is 4x plus 5, and the width is 5x minus 3. Our goal is to write a simplified expression for the unknown height, h of the box. Let's check out the setup visually. Step 1. To find the height, we first need to determine the area of the base. The base area is found by multiplying length times width. Expanding the product of 4x plus 5 and 5x minus 3 using the distributive property, we get 20x squared minus 12x plus 25x minus 15. Combining the middle-like terms simplifies this to 20x squared plus 13x minus 15. Step 2. Finally, we isolate the height h by dividing the total volume by our new base area. We set up the division fraction, 60x cubed plus 119x squared plus 7x minus 60, divided by 20x squared plus 13x minus 15. By performing polynomial division, 60x cubed divided by 20x squared gives 3x, and the remaining constant part gives 4. Our final simplified answer for the height h is 3x plus 4 centimeters. Welcome back. Let's look at the remaining sections of Chapter 6, Manipulating Polynomials. Our upcoming roadmap includes special products, factoring quadratics, and advanced polynomial manipulations. In today's intensive session, we are going to fully cover 5 main sections. We will completely master from Section 6.4 all the way to Section 6.8 in this class. Get ready to dominate special products and factoring polynomial quadratics. Let's explore the geometric meaning of special binomial products. Consider a large square with a total side length of a plus b. We can divide this large square into 4 smaller regions. One square with area a squared, another square with area b squared, and 2 identical rectangles, each with an area of AB. This visually explains the expansion formula. Now let's remember these 3 special binomial products. Given any real numbers a and b, we have 3 core identities. First, the square of a plus b equals a squared plus 2ab plus b squared. Second, the square of a minus b equals a squared minus 2ab plus b squared. And third, a plus b times a minus b perfectly results in a squared minus b squared. When you expand the quantity of a plus b squared, you always get an ab term. Let's check this mathematically using the distributive property. The square of a plus b can be written as a plus b times a plus b. Distributing the terms, we get a squared plus ab plus ba plus b squared. Since ab and ba are identical commutative terms, we combine them into 2ab. This beautifully results in a squared plus 2ab plus b squared. Let's solve a perfect square binomial expansion problem using an area model. Our new example asks us to expand and simplify the quantity 3x plus 2 squared. Geometrically, this is identical to finding the total area of a large square with side length 3x plus 2. Let's visualize this area model on the screen. Step 1. Let's expand this mathematically by putting the expression in the form a plus b times a plus b. The quantity 3x plus 2 squared is equal to 3x plus 2 times 3x plus 2. Now, we expand the parentheses using the distributive property. 3x times 3x is 9x squared, and 3x times 2 is 6x. Then, 2 times 3x is another 6x, and 2 times 2 is 4. Step 2. Finally, let's combine the middle-like terms. Notice that we have 2 identical 6x terms in the middle, just like the 2 rectangles in our area model. Adding 6x and 6x beautifully gives us 12x. Therefore, our fully simplified final trinomial answer is 9x squared plus 12x plus 4. The perfect square binomial problem is completely solved. Let's explore another special product. When you expand a minus b squared, the middle term is always negative. Our new example asks us to expand the quantity 2x minus 3 squared. Geometrically, we find the area of a smaller square inside a large square with side length 2x. Let's visualize this subtraction area model on the screen. Step 1. Let's expand this mathematically using the distributive property. The quantity 2x minus 3 squared can be written as 2x minus 3 times 2x minus 3. Distributing the terms, 2x times 2x gives 4x squared, and 2x times minus 3 is minus 6x. Next, minus 3 times 2x is another minus 6x, and minus 3 times minus 3 beautifully results in positive 9. Step 2. Finally, let's combine the middle-like terms. Notice that we have two identical negative 6x terms in the middle. Combining minus 6x and minus 6x gives minus 12x. Therefore, our fully simplified final trinomial answer is 4x squared minus 12x plus 9. The calculation perfectly matches our geometric model. Let's solve example 2, focusing on the perfect square trinomial with subtraction. Our new problem asks us to expand and simplify the quantity 4y minus 3 squared. In the diagram, 4y minus 3 squared is exactly the same as the area of the darker inner square. Let's visualize this geometric relationship on the screen. Step 1. Put the expression in the form of minus b times a minus b. The quantity 4y minus 3 squared is equal to 4y minus 3 times 4y minus 3. Let's expand the terms step by step. For y times 4y gives 16y squared. For y times minus 3 is minus 12y. Then, minus 3 times 4y is another minus 12y, and minus 3 times minus 3 is positive 9. Step 2. Finally, let's combine the middle-like terms together. Minus 12y beautifully simplifies to minus 24y. Therefore, our fully simplified final trinomial answer is 16y squared minus 24y plus 9. The calculation perfectly matches our geometric model, and the solution is complete. Let's explore how the greatest common factor, or GCF, serves as a divisor. The greatest common factor of a set of monomials is the largest possible divisor of all monomials in that set. To find it, a great strategy is to break down each expression into its smallest prime components and then gather the matching parts shared by all of them. Let's practice example 1 with our brand new set of expressions. Find the greatest common factor of 12a cubed b squared, 16a squared b cubed, and 24a to the fourth b squared. Start by writing down each monomial as a product of the smallest factors possible, expanding the coefficients into prime numbers, and writing out each variable. Now let's list all the numbers and variables that are shared factors of all three terms. They all share two 2's, two a's, and two b's. These are called the common factors. By multiplying these shared pieces together, 2 times 2 times a squared times b squared, we beautifully find our final greatest common factor answer for a squared b squared. Is there a faster way to find the GCF without expanding everything? Yes. You can also find the GCF of two or more monomials by simply multiplying together the GCFs of each of the different parts. Let's apply this shorter method to our same example expressions: 12a cubed b squared, 16a squared b cubed, and 24a to the fourth b squared. Let's break down the problem into different parts. First, the greatest common factor of the coefficients 12, 16, and 24 is 4. Second, consider the variable a, the GCF of a cubed, a squared, and a to the fourth is a squared. Finally, look at the variable b. The GCF of b squared and b cubed is b squared. Now, we simply multiply all of these individual GCF parts together. So, the greatest common factor of 12a cubed b squared, 16a squared b cubed, and 24a to the fourth b squared is 4 times a squared times b squared. This instantly gives us 4a squared b squared. As you can see, both methods yield the exact same answer, but this way is much faster. Polynomials can sometimes be factored too. When a polynomial can be expressed as the product of two or more numbers, monomials or polynomials, those smaller components are called factors of that polynomial. To find the factors, the best first step is to identify the greatest common factor of all the terms. Let's check out our new example expression, 8n to the fourth minus 6n squared. Step 1. Let's find the greatest common factor of our two terms. For 8n to the fourth, the components are 2 times 4 and n squared times n squared. For minus 6n squared, it's minus 2 times 3 times n squared. The shared factor present in both terms is 2 and n squared, so our GCF is 2n squared. Next, rewrite the expression with this factor taken out. This beautifully leaves us with 2n squared times the quantity 4n squared minus 3. Step 2. It's always worth checking your factoring by multiplying out again. Let's distribute 2n squared back into the parentheses using the distributive property. 2n squared times 4n squared is 8n to the fourth. And 2n squared times minus 3 is minus 6n squared. This perfectly returns us to our original expression, proving that our factored answer is 100% correct. Let's look at an alternative method for taking out factors. We will factor the expression 9x cubed minus 6x squared. First, let's find the greatest common factor of the coefficients and the variables. Now, to rewrite the expression, we multiply and divide the whole terms by our greatest common factor, 3x squared. By doing this, we successfully factor out 3x squared, leaving 3x minus 2 inside. This is our final factored expression. We can take out polynomial factors too. Let's look at this expression. Open parenthesis, y plus 3, close parenthesis, times x squared, plus y plus 3 times x, plus y plus 3. Notice that each term contains the exact same polynomial block, y plus 3, as a common factor. To factor this out, we place y plus 3 outside the parentheses, and then divide each original term by y plus 3. This perfectly leaves x squared plus x plus 1 inside the block. We have successfully grouped the entire polynomial factor. Let's learn how to factor a quadratic polynomial. We want to factor the expression x squared plus 7x plus 12. To factor this, we need to find two numbers that multiply together to give 12, and at the same time, add together to give 7. Using these two numbers, 3 and 4, we can write the factored expression as open parenthesis x plus 3 close parenthesis times open parenthesis x plus 4 close parenthesis. To be absolutely sure, if we expand out these parentheses using the distributive property, we get x squared plus 4x plus 3x plus 12, which simplifies back to our original expression. The factors are perfect. If you see a common factor in each term, such as a number or a variable, you must always take it out first. Let's factor this expression, 2x squared plus 14x plus 24. Notice that every single coefficient is divisible by 2. So let's factor out 2 first. Great. Now, the quadratic expression inside the parentheses, x squared plus 7x plus 12, can be factored even further using our previous method. Since 3 and 4 add up to 7 and multiply to 12, it breaks down into x plus 3 times x plus 4. Therefore, our final, completely factored expression is 2 times x plus 3 times x plus 4. When you cannot find a common factor, you need to factor x squared plus bx plus c by trial and error. Let's look at this expression, 2x squared plus 7x plus 3. We must find factors of the leading coefficient 2 and factors of the constant term 3, such that their cross products add up to the middle term, 7. Let's test the combination. We arrange 1x and 2x on the left, and 3 and 1 on the right. Multiplying crosswise, 1x times 1 is 1x, and 2x times 3 is 6x. Adding 6x and 1x gives exactly 7x, which matches the middle term. Therefore, our final factored expression is open parenthesis x plus 3, close parenthesis, times open parenthesis, 2x plus 1, close parenthesis. Let's solve another advanced example. We want to factor 2x squared plus 9x plus 4. First, let's write down the possible factor pairs. For the leading coefficient 2, the pair is 1 and 2. For the constant 4, the pairs could be 1 and 4 or 2 and 2. Let's test which combination gives 9x. The combination that gives exactly 9x is open parenthesis 2x plus 1 close parenthesis times open parenthesis x plus 4 close parenthesis. Let's double check this result by expanding it out. Multiplying the terms gives 2x squared plus 8x plus 1x plus 4, which perfectly matches our original equation. Therefore, our factorization is completely correct. Looking carefully at the signs in the quadratic can help you work much faster. Let's factor this expression, 2x squared plus 11x plus 5. Here, the constant c equals 5, which is positive. This tells us its factors must have the same sign, either both positive or both negative. Now look at the middle coefficient, b equals 11, which is also positive. Because the sum must be positive, the factors cannot be negative. They must be positive. This eliminates the negative options instantly, narrowing our choice to +1 and +5. Therefore, we immediately get the correct combination, 2x plus 1 times x plus 5. Quadratics with two variables can also be factored using the exact same method. Let's factor the following expression x squared plus 6xy plus 5y squared. To fill the gaps, we need two terms that will multiply together to make 5y squared, and at the same time, add together to make 6y. Let's test the expressions that multiply to 5y squared. 5y squared and 1 add up to 5y squared plus 1, which is incorrect. However, 5y and y add together to make exactly 6y. This matches the middle term. So, our final factored expression is open parenthesis x plus 5, y close parenthesis times open parenthesis x plus y close parenthesis. Trial and error can be tricky if there are more possibilities. Let's factor the following complex expression, 3x squared minus 10xy plus 3y squared. First, 3x squared can be factored into 3x and x. To fill the gaps, we need two negative terms in y that multiply to positive 3y squared and cross-multiply to give negative 10xy. Let's try out some sets of parentheses. First, trying 3x minus 3y times x minus y gives cross terms of negative 3xy and negative 3xy, which add up to negative 6xy. This is incorrect. Second, trying 3x minus y times x minus 3y gives cross terms of negative 9xy and negative xy, which add up to exactly negative 10xy. This matches perfectly. So, our final correct factored expression is 3x minus y times x minus 3y. Let's factor the expression x squared minus 49. First, substitute x squared for m squared and 49 for c squared. Since the square root of 49 is 7, we can rewrite it as x squared minus 7 squared. Applying the template, we get x plus 7 times x minus 7. Always watch out for the opposite signs inside the parentheses. The square of a binomial results in a perfect square trinomial. The pattern states that open parenthesis m plus c, close parenthesis squared equals m squared, plus 2mc, plus c squared. Let's see how this structure behaves. Let's factor the perfect square trinomial x squared plus 6x plus 9. First, substitute x squared for m squared and 9 for c squared. The square root of 9 is 3, which perfectly matches our middle term since 2 times 3 equals 6. Applying the equation backwards, we immediately get open parenthesis x plus 3, close parenthesis squared. Sometimes you need to group terms together before you can see any common factors. Let's factor this expression by grouping. For x, plus 7sx minus 8m minus 14sm. First, let's group the first two terms and the last two terms together in parentheses. Next, factor out the common factors from each group. The first group has a common factor of x, leaving 4 plus 7s. The second group has a common factor of negative 2m, also leaving 4 plus 7s. Now you can see another shared common factor block for plus 7s. Using the distributive property, we factor it out to get our final result, x minus 2m times 4 plus 7s. Welcome back, everyone. Today, we are diving into Chapter 7, Quadratic Equations and Their Applications. In this lesson, we will focus specifically on the first three core areas, Section 7.1, Solving Quadratic Equations, Section 7.2, Completing the Square, and Section 7.3, the Quadratic Formula and Applications. Let's get started on mastering these essential algebraic tools. Section 7.1. Quadratic equations have a degree of 2. This means they contain a squared variable, but no higher powers. Let's look at these three fresh examples. Notice that in each unique equation, the highest exponent of the variable is exactly 2. The general form of a quadratic equation is written as ax squared plus bx plus c equals 0, where a, b, and c are numbers and a is not 0. For instance, in our first example, a equals 1, b equals negative 5, and c equals 6. In our second example, a is 3, b is 15, and c is negative 42. One way to solve a quadratic equation is to factor it and then make use of the zero product property. This property states that if the product of two factors m and c equals 0, then either m equals 0, c equals 0, or both must be 0. Let's solve the quadratic equation x squared plus 3x minus 28 equals 0 by factoring. First, we factor the trinomial into x minus 4 multiplied by x plus 7 equals 0. By the zero product property, we set each individual factor to 0. Therefore, either x minus 4 equals 0 or x plus 7 equals 0. This beautifully gives us our final solution, x equals 4 or x equals negative 7. To solve a quadratic equation using factoring, we follow 3 steps. First, arrange all terms so that you have 0 on one side. Second, factor the non-zero expression completely if possible. Third, make use of the zero product property to find the final solutions. Let's apply these steps to an example. Solve x squared minus 2x minus 8 equals 0. The right-hand side is already 0, so we factor the expression on the left. This gives us x plus 2 multiplied by x minus 4 equals 0. By the zero product property, either x plus 2 equals 0 or x minus 4 equals 0. Therefore, our solution is x equals negative 2 or x equals 4. Next, let's explore the square root method. If you square a positive or negative number, you get the exact same answer. Therefore, if we take the square root of a number p, there are always 2 possible answers. In other words, if m squared equals p, then m must equal plus or minus the square root of p. Let's look at an example. Solve the quadratic equation x squared equals 49. To solve this, we can take the square root of both sides. By applying our property, we beautifully find that x is equal to plus or minus 7. We can also solve this exact same equation using the method of factoring. But remember, to use the factoring method, you must first arrange the terms into the form of something equals 0. Only then can you apply the zero product property. Let's solve the equation x squared equals 64 by factoring. First, we subtract 64 from both sides to get x squared minus 64 equals 0. Next, we factor this difference of squares into x plus 8 multiplied by x minus 8 equals 0. Using the zero property, either x plus 8 equals 0 or x minus 8 equals 0. This beautifully results in x equals 8 or x equals negative 8, which means x equals plus or minus 8. Let's look at another application of the square root method. Sometimes, the left-hand side of a quadratic equation forms a perfect square trinomial. In this example, we want to solve 9x squared minus 12x plus 4 equals 16 by taking square roots of both sides. To solve this, we first recognize that 9x squared minus 12x plus 4 factors perfectly into the square of 3x minus 2. This gives us the equation 3x minus 2 squared equals 16. Taking the square root of both sides, we get 3x minus 2 equals plus or minus 4. Now we solve for x. This splits into 2 cases, leading beautifully to our final answers x equals 2 or x equals negative 2/3. Now let's move on to section 7.2, converting binomials to perfect squares. A binomial expression like x squared plus 6x is not a perfect square on its own. However, we can turn it into a perfect square trinomial by adding a specific constant. This constant term is always equal to the square of half of the coefficient of x. Let's look at an example. Convert x squared plus 6x to a perfect square trinomial. First, find the coefficient of x, which is 6. Next, take half of 6 to get 3 and square it. 3 squared gives us 9. Therefore, by adding 9, we beautifully create the perfect square trinomial x squared plus 6x plus 9, which can be factored as the square of x plus 3. Let's formalize the rule for completing the square for x squared plus bx. To convert any expression of the form x squared plus bx into a perfect square trinomial, we always add b over 2 squared. The resulting trinomial can then be written beautifully as the square of x plus b over 2. Let's look at example 2. Form a perfect square trinomial from x squared plus 10x. Here, our coefficient b is equal to 10. So, to complete the square, we add 10 over 2 squared. 10 divided by 2 is 5, and 5 squared is 25. This beautifully gives us x squared plus 10x plus 25, which simplifies perfectly into the square of x plus 5. What if the coefficient of x squared is not 1? With an expression of the form ax squared plus bx, we can still add a number to make it a perfect square. Let's look at this specific puzzle. If 2x squared minus 12x plus m is equal to 2 times the square of x plus d, what is m? To solve this, we first multiply out the right-hand side. Expanding 2 times x plus d squared gives us 2x squared plus 4dx plus 2d squared. Next, we equate the coefficients of x. This gives us negative 12 equals 4d, meaning d must be negative 3. Finally, we compare the constant terms. M equals 2d squared. Substituting negative 3 into d, we get m equals 2 times 9, which beautifully results in m equals 18. Now let's look at writing an expression of the form x squared plus bx plus c into the vertex form, x plus k squared plus m. To build our foundation, recall how we convert the binomial part, x squared plus bx, into a perfect square trinomial by adding the square of b over 2 to it. Let's try a foundational example. Convert x squared plus 12x to a perfect square trinomial. Here, our coefficient b is 12. So, to complete the square, we find half of 12, which is 6, and square it. 6 squared is 36. By adding 36, we beautifully form the perfect square trinomial x squared plus 12x plus 36, which is exactly equal to the square of x plus 6. More general quadratic expressions can also be written in this form. To do this, first take just the first 2 terms and add the square of half of b. Second, rewrite the binomial by subtracting that same added value to keep it balanced. Third, add the original constant c to complete the vertex form expression. Let's solve example 3. Express x squared plus 6x plus 2 in the form x plus k squared plus m. First, looking at the first two terms, b is 6, so we add 3 squared, which is 9. This gives us the perfect square part, x plus 3 squared. To balance the expression, we must subtract 4, then add our original constant c, which is 2. Combining -9 and plus 2 beautifully results in our final answer, x plus 3 squared minus 7. This is the most general case you can meet. Writing ax squared plus bx plus c in the form a times the square of x plus k plus m. First, factor out the coefficient from the first two terms. Second, complete the square inside the parentheses by adding and subtracting the square of half of the x coefficient. Third, distribute it back and combine the remaining constant terms. Let's look at example 5 with fresh numbers. Write 2x squared plus 8x plus 11 in the form a times x plus k squared plus m. First, factor out 2 from the first two terms to get 2 times open parenthesis x squared plus 4x close parenthesis plus 11. Second, add and subtract 4 inside the parenthesis since half of 4 squared is 4. This gives us 2 times the square of x plus 2 minus 8. Finally, combining -8 and plus 11 beautifully results in our final answer, 2 times the square of x plus 2 plus 3. Now let's apply our techniques to solve an actual quadratic equation by completing the square. First, take the constant term onto the right-hand side of the equation. Second, convert the left-hand side to a perfect square trinomial by adding the square of half the coefficient of x to both sides. Third, rewrite the left side as a perfect square and solve using the square root method. Let's solve example 1 with fresh numbers. Solve x squared minus 6x plus 5 equals 0. First, we move plus 5 to the right side to get x squared minus 6x equals -5. Next, half of -6 is -3, and squaring it gives 9. Add 9 to both sides. This simplifies to x squared minus 6x plus 9 equals 4. Factoring the left side, we get the square of x minus 3 equals 4. Taking the square root, x minus 3 equals plus or minus 2. This splits into two simple equations, beautifully leading to x equals 5 or x equals 1. Let's solve a more complex quadratic equation by completing the square. First, rearrange the equation so that all like terms are combined on the left-hand side. Then, if the coefficient of x squared is not 1, divide the entire equation through by that number to make it 1. To solve this, we first bring all terms to the left side, which gives us 2x squared plus 6x minus 40 equals 0. Next, divide the entire equation by 2 so that the x squared coefficient becomes 1, yielding x squared plus 3x minus 20 equals 0. Then, move the constant 20 to the right side and complete the square by adding 9 over 4 to both sides. This beautifully results in the square of x plus 3 over 2 equals 89 over 4. Taking square roots and isolating x, we find our final solution x equals -3 plus or minus the square root of 89, all over 2. Welcome to section 7.3. Today, we will discuss how quadratic equations can be in any variable. A lot of the equations you see may contain a variable other than x, such as y, z, or t. However, they are still quadratic equations and can be solved in the exact same way because the mathematical structure remains completely unchanged. Let's look at an example. Find the solutions of the following two quadratic equations. Equation A is x squared minus 5x plus 4 equals 0. Equation B is z squared minus 5z plus 4 equals 0. For equation A, it factors into x minus 4 times x minus 1 equals 0, giving x equals 4 or 1. For equation B, the variable is z rather than x, but it factors the exact same way into z minus 4 times z minus 1 equals 0, giving z equals 4 or 1. As you can see, both equations are really identical, only the letters have changed. The quadratic formula solves any quadratic equation in standard form. The solutions to the equation ax squared plus bx plus c equals 0 are given by x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. We can derive this powerful formula by applying the method of completing the square. Let's trace the algebraic derivation. We start with the equation ax squared plus bx plus c equals 0. First, move the constant c to the other side. Next, divide the entire equation by a so the leading coefficient is 1. To complete the square, we add the square of b over 2a to both sides. This gives us the square of x plus b over 2a equals b squared minus 4ac over 4a squared. Taking the square root of both sides brings in the plus or minus sign. Finally, isolating x gives us our completed formula. Let's practice a core application example using the quadratic formula. To solve the equation x squared minus 3x minus 10 equals 0, we first list out the exact values of a, b, and c. Here, a equals 1, b equals negative 3, and c equals negative 10. Now, we carefully substitute these three numbers into our formula. Substituting our values, x equals negative 3 plus or minus the square root of negative 3 squared minus 4 times 1 times negative 10, all divided by 2 times 1. Simplifying inside the root, we get 3 plus or minus the square root of 9 plus 40, which is 49. Since the square root of 49 is 7, this reduces beautifully to 3 plus or minus 7 over 2. Splitting into two cases, 3 plus 7 over 2 gives 5, and 3 minus 7 over 2 gives negative 2. Therefore, our answers are x equals 5 or x equals negative 2. Let's practice another advanced example using the quadratic formula. To solve the equation 2x squared minus 7x plus 4 equals 0, we first list out the exact values of a, b, and c. Here, a equals 2, b equals negative 7, and c equals 4. Now, we carefully substitute these three numbers into our formula. Substituting our values, x equals negative 7 plus or minus the square root of negative 7 squared minus 4 times 2 times 4, all divided by 2 times 2. Simplifying inside the root, we get 7 plus or minus the square root of 49 minus 32, which is 17. Since 17 is not a perfect square, The square root of 17 remains in our final expression. Therefore, our final answers are 7 plus the square root of 17 over 4, or 7 minus the square root of 17 over 4. Let's solve a word problem using the quadratic formula. The difference between a pair of numbers is 5, and their product is 150. If we call the lower number x, then the higher number must be x plus 5. Multiplying them gives the equation x times open parenthesis x plus 5 close parenthesis equals 150. Rearranging it to standard form gives x squared plus 5x minus 150 equals 0. Now, we identify a equals 1, b equals 5, and c equals negative 150. Substituting these into the quadratic formula, x equals negative 5 plus or minus the square root of 5 squared minus 4 times 1 times negative 150, all divided by 2. The inside of the root becomes 25 plus 600, which is 625. The square root of 625 is 25. This gives two cases for x, resulting in x equals 10 or x equals negative 15. Adding 5 to each to find the higher numbers, our final pairs are 10 and 15, and negative 15 and negative 10. Welcome back to class. Today, we are moving forward in Chapter 7, Quadratic Equations and Their Applications. In this specific lesson, we will cover the remaining 3 core areas, Section 7.4, Quadratic Graphs, Section 7.5, the discriminate, and Section 7.6, motion tasks and other applications. Let's focus on these advanced algebraic concepts. Section 7.4. The graph of any quadratic function forms a smooth curve called a parabola. When the coefficient is positive, the parabola opens upward, forming a U-shape. When it is negative, it opens downward, forming an N-shape. Every parabola is perfectly symmetric across its vertical line of symmetry. Now, let's explore how the exact size of a changes the graph. A bigger value of the absolute value of a results in a steeper or narrower parabola. For instance, notice how the blue graph of y equals 2x squared is much steeper and narrower than the original red graph of y equals x squared. Section 7.4. The graph of y equals ax squared plus c has the exact same shape as y equals ax squared. The only difference is its vertical position. Adding a constant c moves the entire parabola up or down along the y-axis. Let's look at these fresh examples on our coordinate plane. An important property of these graphs is how they cross the x-axis. The points where the graph crosses the x-axis are called the x-intercepts or roots. For example, y equals x squared minus 9 crosses the x-axis at exactly plus or minus 3. However, the graph y equals x squared plus 2 never crosses the x-axis at all, because the equation x squared plus 2 equals 0 has no real solutions. Section 7.4. To accurately graph any quadratic function of the form y equals ax squared plus bx plus c, there are 3 essential features you need to find. First, find the x-intercepts by solving the quadratic equation when y equals 0. Second, find the y-intercept by setting x equal to 0. Third, determine the exact position of the vertex. Let's look at example 1 with fresh numbers. Sketch the graph of y equals x squared minus 4x plus 3. First, setting y to 0 gives the roots x equals 1 and x equals 3, which are our x-intercepts. Second, setting x to 0 gives y equals 3, our y-intercept. Third, completing the square reveals the vertex is at the point 2, -1. Now, let's watch these key elements form a beautiful parabola on the left. Section 7.4. Let's try to sketch the graph of y equals x squared minus 4x plus 5. First, if we attempt to find the x-intercepts by applying the quadratic formula, we notice something unusual. The value inside the square root becomes -4. Since we cannot take the square root of a negative number in real numbers, this tells us the function has no real roots and never crosses the x-axis. But this doesn't mean that we cannot graph it. We just need a different method. The trick is to complete the square to find the vertex. Rewriting the equation gives y equals x minus 2 squared plus 1, which clearly shows our vertex is located at the point 2, 1. Let's look at the left to see this parabola opening upward, completely above the x-axis. Section 7.5. We can use the quadratic formula to find the x-intercepts of a parabola. By setting y equal to 0, finding the solutions to the quadratic equation allows us to see exactly where the graph crosses the x-axis. In fact, the value of b squared minus 4ac under the radical tells us a lot about these solutions. However, it is sometimes impossible to get a real answer from the formula. When b squared minus 4ac is negative, we cannot take the square root of that number. Geometrically, this means that the function has no real roots, and the graph of the parabola never crosses the x-axis at all. Section 7.5. Let's describe the nature of the solutions for the equation 2x squared minus 5x minus 3 equals 0 and find their exact values. First, listing our coefficients gives a equals 2, b equals -5, and c equals -3. Calculating the discriminant b squared minus 4ac results in 49. Since 49 is positive, the equation has two distinct real solutions. Applying the quadratic formula, we find x equals 3 or -1/2. Because our discriminant was positive, the corresponding function graph must cross the horizontal x-axis at exactly 2 places. These cross points match our calculated roots perfectly. Let's look at the left coordinate plane. You can clearly observe the blue parabola passing through 3, 0, and -0.50. Section 7.5. Next, let's explore what happens when b squared minus 4ac equals 0. If the discriminant is exactly 0, then the solutions of the quadratic equation are real and equal to each other. This is also commonly called a double root. Graphically, it means the parabola just touches the x-axis in one place. Let's look at example 3 with creative new numbers. Determine the nature and find the values of the solutions for x squared minus 4x plus 4 equals 0. Computing b squared minus 4ac gives negative 4 squared minus 16, which is 0. This tells us the equation has a double root. Factoring reveals the single solution x equals 2. On the left, you can watch the blue parabola touch the x-axis perfectly at the point 2, 0. Section 7.5. Let's finish our discriminate case studies by looking at what happens when b squared minus 4ac is less than 0. If the discriminate is negative, the quadratic has no real solutions, and the function has no real roots. Graphically, this means the parabola never intersects, crosses, or touches the x-axis. Let's describe the graphs for two creative examples. Equation A is x squared minus 2x plus 2. Its discriminate is negative 4, and since is positive, the graph is concave up and stays entirely above the x-axis. Equation B is negative x squared plus 4x minus 5. Its discriminate is also negative 4, but since it is negative, the graph is concave down and stays entirely below the x-axis. Section 7.6. Quadratic functions can beautifully describe motion under gravity. Suppose the height of a stone thrown up in the air is modeled by the equation h equals 96t minus 16t squared. We want to find out after how many seconds is the stone at a specific height of 128 feet. Let's solve this quadratic application puzzle. To solve this, we first rewrite the equation in standard form, giving 16t squared minus 96t plus 128 equals 0. Next, we divide through by 16 to simplify the equation, which yields t squared minus 6t plus 8 equals 0. Factoring this quadratic equation gives open parenthesis t minus 2 close parenthesis times open parenthesis t minus 4 close parenthesis equals 0. By the zero product property, we find t equals 2 or t equals 4. So the stone reaches 128 feet after 2 seconds on the way up, and again after 4 seconds on the way down. Section 7.6. Let's analyze an advanced word problem. The height of a ball in feet after t seconds is given by the function h equals negative 16t squared plus 64t plus 80. First, let's explain what the h-intercept and t-intercept mean in this context. The h-intercept represents the initial height of the ball before release, which is 80 feet. The t-intercept indicates the time when the ball hits the ground, which is 5 seconds. Now let's find the maximum height reached by the ball. To do this, we rewrite our function into the vertex form by completing the square. This gives h equals negative 16 times the square of t minus 2 plus 144. This clearly reveals that the vertex is at the point 2, 144. Therefore, the ball reaches its maximum height of 144 feet after exactly 2 seconds. Let's look at the left to watch this stunning parabola launch from 80 feet, hit peak, and fall down. Welcome back to class. Today, we are moving forward in Chapter 8, Rational Expressions and Functions. In this lesson, we will focus on the first 3 core areas, Section 8.1, Rational Expressions, Section 8.2, multiplying and dividing rational expressions, and Section 8.3, adding and subtracting rational expressions. Let's master these foundational algebraic concepts. A rational expression is any expression that can be written in the form of a fraction. This means it always has a numerator and a denominator. For example, look at this form, p over q, where q cannot be 0. An expression is undefined if the denominator is equal to 0. Let's look at an example. Determine the value of x for which the expression 5 over x minus 3 is undefined. It is undefined when the denominator, x minus 3, equals 0. This means that the expression is undefined when x equals 3. Let's look at another example with a quadratic denominator. Determine the values of x for which the expression 4x over x squared minus 3x minus 10 is undefined. To solve this, we first need to factor the denominator. The quadratic expression x squared minus 3x minus 10 factors into the product of x minus 5 and x plus 2. The expression becomes undefined when the denominator equals 0. This happens when either x minus 5 equals 0 or x plus 2 equals 0. Therefore, the expression is undefined when x equals 5 or x equals negative 2. Let's look at an example with rational expressions containing a variable. Determine whether the expressions 3x over 4 and 9x over 12 are equivalent. To test equivalence, we can use the cross-multiplication rule. The expressions are equivalent if the product of A and D equals the product of B and C. Multiplying 3x by 12 gives 36x. Multiplying 4 by 9x also gives 36x. Since both cross products are equal to 36x, the two expressions are equivalent. A rational expression can be written in its lowest terms by reducing it to the simplest equivalent fraction. This is done by factoring both the numerator and denominator, and then canceling out the common factors. Let's practice with an example. Reduce the expression 42 over 48y to its lowest terms. First, find the greatest common factor of 42 and 48, which is 6. This means we can rewrite 42 as 7 times 6 and 48y as 8 times 6 times y. By canceling out the common factor, 6, we get the simplest equivalent fraction, 7 over 8y. Factoring both the numerator and the denominator is the absolute key to solving more complicated rational expressions. Breaking it down into its factors helps us easily spot the common terms that can be canceled out. Let's solve a new example. Simplify the expression x squared minus 16 over 5x minus 20. First, let's factor the numerator. X squared minus 16 is a difference of squares, which factors into x minus 4 times x plus 4. Next, the denominator, 5x minus 20, factors into 5 times x minus 4. Notice that x minus 4 is a common factor in both parts. By canceling out x minus 4, we get the final simplified result, x plus 4 over 5. Now let's move on to section 8.2, multiplying rational expressions. To multiply two rational expressions, we simply multiply the numerators together and multiply the denominators together. However, it is always best to factor and cancel common terms before multiplying. Let's look at an example. Simplify the product of xy over 3x plus 6y times 4x plus 8y over x squared y. First, let's factor everything. The first denominator factors into 3 times x plus 2y. The second numerator factors into 4 times x plus 2y. Now, we can cancel out the common terms. The group x plus 2y cancels out completely. 1x and 1y from the top and bottom also cancel out. After multiplying the remaining parts, we get our final answer for over 3x. Let's tackle a more advanced problem. Simplify the product of these three rational expressions. It looks intimidating, but the strategy remains exactly the same. We will factor every single numerator and denominator first. To solve this, let's factor each part step by step. Notice how the quadratics factor beautifully into linear binomials. The grouping method in the second denominator gives us x plus 3 times a minus 2. After writing everything in factored form, we can cancel out all the common factors. The terms x plus 2, x plus 3, and a plus 3 cancel out from the top and bottom. Finally, we are left with the simplified equivalent fraction, a plus 4 times x plus 5 over 2 a minus 1 times a minus 2. Dividing by a fraction is the exact same as multiplying by its reciprocal. For example, let's think about dividing 12 by 1 over 3. This asks, how many thirds are in 12? The answer is 36, which is equivalent to 12 times 3. We can extend this exact same concept to any rational expression. To divide m over c by b over v, we flip the second fraction to its reciprocal, v over b, and change the operation to multiplication. This gives us the final multiplied form, mv over cb. Let's practice dividing rational expressions with polynomials. Simplify the expression x squared minus 9 over x squared minus 4x plus 3, divided by 3x over x minus 1. First, rewrite the division as a multiplication by the reciprocal of the divisor. So we flip 3x over x minus 1 into x minus 1 over 3x. Next, factor all numerators and denominators completely. X squared minus 9 becomes x minus 3 times x plus 3. The quadratic denominator factors into x minus 3 times x minus 1. Now, cancel out all the common factors. The groups x minus 3 and x minus 1 cancel out completely from the top and bottom. Finally, we get the simplified result, x plus 3 over 3x. You can divide any number of rational expressions at once. If there are no parentheses, you must always calculate from left to right. This means each division turns into multiplying by its reciprocal step by step. Let's look at an example. Simplify this long string of divisions. First, rewrite each division as a multiplication by the reciprocal. The second fraction flips, and the third fraction flips too. Next, factor all numerators and denominators completely to see the factors. Finally, cancel out all the common factors from the top and bottom. After dividing out the identical terms, we get the beautifully simplified answer, 3 over x plus 1. You can multiply and divide rational expressions at the same time. Again, work from left to right. Wherever you see a division symbol, change it to multiplication by flipping that specific fraction to its reciprocal. Let's solve the example. First, rewrite the division as a multiplication by the reciprocal. Notice that only the third fraction flips. Next, factor all numerators and denominators completely using quadratic methods. Finally, cancel out all identical common factors from the top and bottom. After dividing out everything, we get the beautifully simple answer, x over y. Welcome to section 8.3, Adding and Subtracting Rational Expressions. To add or subtract expressions with the same denominator, simply add or subtract the numerators and keep the common denominator. For example, look at these general algebraic rules. Let's practice with an example. Simplify the expression x plus 3 over y plus 3x minus 7 over y. Since the denominators are both y, we can add the numerators directly. Combining the terms gives us x plus 3x minus 7 all over y. Next, combine the like terms in the numerator. X plus 3x equals 4x and 3 minus 7 equals negative 4. This gives us our final simplified answer for x minus 4 over y. Let's practice subtracting rational expressions with a common denominator. Subtract and simplify the expression for x plus 2 over x squared minus 16 minus 3x plus 6 over x squared minus 16. Subtract the numerators and keep the common denominator. Be very careful to put a parenthesis around the entire second numerator so the negative sign distributes properly. This gives us 4x plus 2 minus 3x minus 6. Combining like terms simplifies the numerator to x minus 4. Next, factor the denominator. X squared minus 16 factors into x minus 4 times x plus 4. Finally, cancel out the common factor, x minus 4, from the top and bottom. We get our final simplified answer, 1 over x plus 4. When adding fractions with different denominators, you must find a common denominator first. Simply multiply the denominators together to get the common base. Then, convert each fraction into an equivalent fraction with this new common denominator. Let's look at an example. Add 3 over 4 and 1 over 7. Multiply the denominators 4 and 7 to get the common denominator, 28. Convert the first fraction by multiplying the top and bottom by 7, which gives 21 over 28. Convert the second fraction by multiplying the top and bottom by 4, which gives 4 over 28. Now that the denominators are the same, add the numerators. 21 plus 4 equals 25. Our final answer is 25 over 28. Let's practice subtracting rational expressions with different numeric denominators. Subtract and simplify the expression 3x minus 2 over 3 minus 2x plus 4 over 4. First, find a common denominator by multiplying 3 and 4, which is 12. Convert each fraction into an equivalent fraction with 12 as the denominator. Multiply the first fraction by 4 and the second fraction by 3. Now, combine them over the common denominator 12. Be careful to distribute the negative sign into the entire second numerator. This gives us 12x minus 8 minus 6x minus 12. Finally, combining the like terms gives us the answer, 6x minus 20 over 12. We can factor out a 2 from the top to reduce the fraction to 3x minus 10 over 6. To add or subtract fractions with different denominators efficiently, we need to find the least common multiple, or LCM, of the denominators. First, factor the denominators completely. Then, multiply together the highest power of each factor that appears. Now, let's look at the 4 steps to add or subtract fractions with different denominators. Step 1. Find the least common multiple of the denominators. Step 2. Convert each fraction into an equivalent fraction with the LCM. Step 3. Add or subtract the numerators. And Step 4. Factor and cancel any common factors if possible. Let's solve an advanced problem combining addition and subtraction. Simplify the expression 3 over 2x plus 4 plus 2 over 3x minus 3 minus 4 times x plus 2 over x squared plus x minus 2. First, factor all the denominators completely to find the least common denominator. The denominators are 2 times x plus 2, 3 times x minus 1, and the product of x plus 2 and x minus 1. So, the least common denominator is 6 times x plus 2 times x minus 1. Convert each fraction using this common denominator and combine the numerators. Distribute the numbers and combine the like terms in the numerator. This simplifies to 13x minus 25. Our final simplified answer is 13x minus 25 over 6 times x plus 2 times x minus 1. Welcome back to class. Today, we are continuing our journey in Chapter 8, Rational Expressions and Functions. In this final lesson of the chapter, we will master the remaining 2 core areas, Section 8.4, Solving Equations with Fractions, and Section 8.5, Relations and Functions. Let's focus on finishing this chapter strong. When solving a fractional equation, we must consider its limitations. A fractional equation is undefined when the denominator of any expression equals 0. This means there are strict limitations on what values the solution can be. Let's look at an example. Consider the fractional equation 2 over 2x minus 3 equals 3 over x plus 4. To find the limitations on x, we set both denominators so they cannot equal 0. Therefore, 2x minus 3 cannot be 0, and x plus 4 cannot be 0. Solving these shows that x cannot equal 3 over 2, and x cannot equal negative 4. When solving fractional equations with different denominators, we can multiply the entire equation by the least common multiple of the denominators. This allows all the denominators to be cancelled out completely, making the equation much easier to solve. Let's solve an example. Consider this fractional equation. To clear the fractions, multiply both sides by the least common multiple, which is 6 times 2x minus 3 times x plus 4. Canceling the denominators yields 2x minus 3 times x plus 4 plus 6 times x plus 4 equals 6 times 2x minus 3. Expanding and simplifying both sides transforms it into a quadratic equation, which allows us to solve for x cleanly. Let's solve a complete fractional equation. Look at this expression. The question asks us to solve it, but first, we must state any values for which the equation is undefined. Since denominators cannot be 0, x plus 1 and x minus 1 cannot be 0. This gives us our initial limitations: x cannot equal negative 1 or 1. Now let's solve the equation by clearing the fractions. Multiply both sides by the least common multiple, x plus 1 times x minus 1. This clears the denominators and gives us 2 times x minus 1 minus 3 times x plus 1 equals negative 1 times x squared minus 1. Expanding and rearranging the terms leads to the quadratic equation x squared minus x minus 6 equals 0. Factoring this equation gives x minus 3 times x plus 2 equals 0. So, the possible solutions are x equals 3 or x equals negative 2. Since neither of these values violates our initial limitations, both 3 and negative 2 are the true final solutions. Now let's move on to section 8.5, Relations and Functions. An ordered pair is a set of two numbers written in the form x, y. A relation is simply any set of these ordered pairs. For example, let's look at this specific relation named R. Every relation has a domain and a range. The domain is the set of all the first elements or x values of each ordered pair. For our relation R, the domain is 1, 2, 3, and 4. The range is the set of all the second elements or y values. For R, the range is 4, 7, 10, and 13. Notice that these values follow the linear rule, y equals 3x plus 1. One powerful way to visualize a relation is to use a mapping diagram. In this diagram, the area on the left always represents the domain, while the area on the right represents the range. The arrows show exactly which member of the domain is paired with which member of the range. Let's look at a creative example. This mapping diagram represents the relation f. Our domain contains 1, 4, and 7, and our range contains y, w, and k. Following the arrows, 1 maps to y, 4 maps to w, and 7 maps to k. This gives us the complete set of ordered pairs for relation f. Relations can also be plotted on a coordinate plane. Here, the domain is represented on the x-axis and the range on the y-axis. Graphs are most useful when you have continuous sets of values, allowing you to connect points with a smooth curve or a straight line. Let's look at a creative example. This graph represents a continuous relation. The relation is defined by y equals 1 over 2x plus 1. The domain is restricted from -4 to +6. Notice how the solid line smoothly connects the starting point and the ending point. A relation is any set of ordered pairs without restriction. However, a function is a special type of relation. In a function, no two ordered pairs can have the same x value, but different y values. This means each member of the domain maps to a unique member of the range. Let's compare these two diagrams to see the rule in action. On the left, each input maps to exactly one output. This is a function. On the right, notice how the input 2 splits and maps to both a and b. Because one x value goes to two different y values, this relation is not a function. Let's practice determining whether a mapping diagram represents a function. Look at mapping A. Our domain elements are 1, 3, 5, and 9. Notice how the input 3 splits and maps to both x and z. Because this single x value has two different y values, mapping A is not a function. Now let's examine mapping C. Our inputs are the same, but the arrows are different. Notice that every single member of the domain maps onto exactly one member of the range. Since no x value branches out to multiple outputs, mapping C successfully represents a true function. Let's practice expressing a function given as a set of ordered pairs into an equation. Look at this function f. It consists of pairs 1, 1, 2, 8, 3, 27, and 4, 64. Let's find the mathematical relationship between the x values and y values. Let's look at the solution. Notice that 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, and 4 cubed is 64. Therefore, the relationship between x and y is y equals x cubed. The domain is simply the set of first elements, 1, 2, 3, and 4. Combining these facts, we can write the function in formal set notation as shown in red below. Think of a function as a rule or a machine. It takes an input value x from the domain, processes it according to a specific rule, and then outputs a single distinct value, f of x, in the range. Let's visualize this process using a creative function machine. When referring to a particular value of a function, you simply replace the x with that relevant number. In our machine, replacing x with 4 gives f of 4, which equals 14. Similarly, you can substitute whole expressions into a function. For example, if we replace x with x plus 5, the expression becomes 3 times the group x plus 5 plus 2. Let's solve an example to find the range of a function given its domain. If p of x equals x cubed minus 2, let's find the range of p of x when the domain is the discrete set -2, -1, 0, 1, and 3. Let's look at the solution. The range is the set of all values of p of x for each x in the domain. So, the range equals the set containing p of -2, p of -1, p of 0, p of 1, and p of 3. Substituting each value into x cubed minus 2 gives the specific calculations. Evaluating these numbers, we find the final range is -10, -3, -2, -1, and 25. Let's learn about the equality of functions. A function f is equal to another function g if and only if their sets of ordered pairs are completely identical. This means it is not enough for their equations to be equivalent. They must also share the exact same domain and range. Let's look at an example with a creative twist. We have two functions, f and g. Function f is defined by x squared minus 9, and function g is defined by x minus 3 times x plus 3. Both functions share the exact same domain set, -2, 0, 1, and 3. Since their equations are algebraically equivalent and their domains are identical, the two functions are completely equal. Finally, by substituting these domain values, we find the range of f to be -5, -9, -8, and 0. Let's solve an advanced rational function problem. Suppose v of x equals x squared plus 2 over x minus 2. First, let's state any restrictions on x. The function is undefined when its denominator, x minus 2, is 0. So x cannot equal 2. Let's look at the graph of this function on the left to see the restriction. Now for part b, let's evaluate v of -2. Substitute x equals -2 into the function. The numerator becomes -2 squared plus 2, which equals 4 plus 2, or 6. The denominator becomes -2 minus 2, which is -4. Dividing 6 by -4 and reducing the fraction yields our final answer, -3 over 2. Let's tackle an advanced function challenge, which forms the core foundation of calculus. Given that g of x equals x squared plus 2, find the difference quotient, g of group x plus h, minus g of x, all over h, in terms of x and h. Let's look at the geometric meaning on the left graph. This expression represents the slope of the secant line connecting two points with a horizontal distance of h. Now let's expand and simplify the difference quotient step by step. First, substitute the function rules into the numerator. G of x plus h becomes the group x plus h squared plus 2. Next, expand the squared group into x squared plus 2xh plus h squared. Notice that x squared minus x squared and 2 minus 2 completely cancel out. This leaves us with 2xh plus h squared over h. By factoring out h from the numerator, we can cancel h from both top and bottom. Our beautifully simplified final answer is 2x plus h.